Before space had a place to exist, before time had a first second, the universe may have erupted from nothing. But was it truly nothing? Or does the Big Bang reveal that nothing was never empty at all? The greatest mystery in science may not be how the cosmos changed, but why reality was ever possible. At the edge of every equation waits a threshold. Not darkness, not emptiness, but a problem language can barely approach. The story begins where intuition fails, because our most familiar image of absence already contains more than it admits. A silent chamber has dimensions, a black horizon has distance, and an empty stage still awaits something to enter. Even the word before may smuggle in a clock, quietly placing events in an order that nature never promised. Yet this is not a retreat from evidence. It is where the evidence becomes most astonishing. Across the observable sky, ancient signals arrive with a precision that turns distant light into a cosmic archive. They tell of expansion, searing temperatures, and a young universe whose earliest accessible moments still shape every galaxy. But their testimony does not automatically settle what, if anything, stands beyond the boundary of that record. The Big Bang is often pictured as a cosmic detonation, a fireball bursting outward through an already waiting arena. The reality is stranger, more elegant, and far less comfortable for the imagination that seeks a familiar beginning. Space itself may be part of the drama, while time may be less a backdrop than an unfolding clue. To follow that clue, we must separate what the universe has revealed from what our metaphors merely suggest. We will begin by stripping away the images that make absence seem simple. The void, the vacuum, the silent black expanse. Each carries hidden furniture, from geometry and fields to rules, possibilities, and the perspective needed to name it. Then we will turn outward, toward the measurements that transformed a philosophical puzzle into a rigorous investigation. Light stretched across immense distances, relic radiation lingering from infancy, and the chemistry of the first minutes form a converging trail. These clues do not show us a first instant directly, yet they reveal a universe with an extraordinary early history. As the trail approaches its limit, our best theories begin to speak in different and sometimes incompatible voices. Relativity describes a pliable space-time shaped by energy and motion, but it eventually confronts conditions beyond its command. Quantum physics reveals restless foundations beneath apparent stillness, yet its language also assumes structures that demand explanation. There, in the tension between these triumphs, lies a frontier where space, time, and cause may no longer behave as expected. Can a beginning occur when there is no earlier moment from which to measure its arrival? The question reaches deeper than chronology. It tests whether cause and effect can survive without time beneath them. Some proposals imagine a smooth cosmic origin, others a transition from a prior phase, and others an ever wider reality. None earns belief through grandeur alone. Every vision must answer to mathematics, observation, and the stubborn details written across the sky. We will enter the quantum realm, where emptiness can possess energy, fluctuations, and measurable consequences without becoming absolute non-existence. We will examine daring models that replace a single origin with a boundary, a bounce, or an uncharted continuation. And we will ask what survives when every model, however powerful, rests upon laws it did not create. This is not a search for a comforting answer, nor an invitation to mistake mystery for magic. It is an encounter with the limits of explanation, and with the remarkable fact that limits can still teach us. On this journey, telescopes become time machines, equations become maps, and silence becomes a test of our deepest assumptions. We will watch the universe cool from unimaginable extremes, assemble the first simple elements, and seed the architecture of stars. We will trace faint patterns in ancient radiation, then follow them into the immense web of modern galaxies. We will stand at the threshold where known physics loses its footing, not in defeat, but in disciplined wonder. Beyond that threshold lie ideas both audacious and constrained, possibilities that may reshape the question before they answer it. Philosophy will not arrive as an escape from science, but as its necessary companion at the farthest edge. For when we ask why anything exists, we also ask what counts as an explanation, and where explanation can end. The answers may remain incomplete, but the evidence is real, the questions are precise, and the stakes are immense. Somewhere between the oldest light we can observe and the deepest assumptions we can name, a new perspective is waiting. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From the first evidence of cosmic expansion to the frontiers of quantum gravity, this journey follows the clues without pretending certainty. The destination is not an easy origin story. It is a sharper vision of what the universe permits us to ask. We begin by leaving the universe behind, stripping away each layer that makes existence seem imaginable and secure. First, galaxies recede, their crowded islands of stars becoming faint embers against a darkness that already conceals assumptions. Spiral arms unwind into dust-like glimmers, while giant elliptical galaxies lose their soft golden halos and sink beyond any horizon we can picture. Then stars vanish, removing furnaces, light, planets, chemistry, and the patient clocks built from changing things around us. The constellations dissolve without sound, and every distant sun disappears with its orbiting worlds, frozen moons, and possible witnesses. Planets follow, taking landscapes, bodies, memory, and every familiar place where questions can be asked aloud by anyone. No ocean reflects a sky, no mountain casts a shadow, and no surface remains beneath an observer's imagined feet. Matter itself dissolves next, with atoms, nuclei, electrons, and the particles beneath them removed from our mental stage. The solid certainty of a hand, a stone, or a human face depends on electromagnetic forces and quantum patterns that would now be gone. Yet apparent darkness remains, and that survival reveals how quickly imagination mistakes an empty picture for nothing itself. We instinctively paint nothing as black, as though the final answer were an enormous unlit room. Darkness looks like absence only because something remains for absence to be measured against within a physical frame. It presumes space, possible paths for light, and conditions under which an observer could register missing illumination there. A black void is therefore not an answer but a stage, containing extension, direction, duration, and the rules that let emptiness appear meaningful to us at all. Now remove that stage as well. Remove the distance between imagined points, the direction in which a thought might travel, and the interval during which anything could wait. Remove the blackness, because blackness is still a visual quality, and visual qualities require a framework in which light can be absent. What remains cannot be pictured as a darker void, a colder region, or an infinite blank expanse. An expanse has size, while absolute nothing would have no size to extend across. It would have no edges, no center, no surrounding darkness, and no hidden silence behind the silence. Even silence assumes time passing without a sound, which is already far more than nothing. Ordinary emptiness never approaches this imagined limit, even when rooms, containers, and landscapes seem completely cleared of contents. An empty room still holds air, heat, stray photons, gravity, electromagnetic fields, microorganisms, walls, and surrounding cosmic radiation. Sunlight may enter through a crack, while infrared radiation streams from warm surfaces and molecules collide invisibly throughout the air. Remove the air, and the chamber still possesses dimensions, measurable intervals, material boundaries, and physical conditions governing experiments. Its gauges can record pressure, its surfaces can absorb radiation, and its clocks can continue marking time. Remove its walls, and the larger region remains filled with radiation, fields, particles, and gravitational relationships of matter. Even intergalactic space contains sparse atoms, ancient light, neutrinos, dark matter, expanding geometry, and quantum fields at minimum. Between great galaxy clusters, matter can become astonishingly thin, with only a few particles scattered through volumes that dwarf entire solar systems. Yet thinness is not non-existence. The faint afterglow of the early universe crosses those regions, and invisible gravitational influence still shapes the trajectories of passing matter. Its near emptiness is a remarkable physical environment, not the non-existence imagined when language casually says nothing at all. The word empty is useful in ordinary speech, but nature is rarely as vacant as our language suggests. Science calls the most carefully evacuated condition a vacuum, but vacuum names a state rather than absolute absence. In laboratories, engineers create extreme vacuums by removing gas molecules until collisions become exceptionally rare. Such chambers allow delicate instruments to operate, imitate portions of space, and reveal physical effects normally hidden by air. Still, a laboratory vacuum contains equipment, boundaries, fields, radiation, and a surrounding space-time in which measurements remain possible. A vacuum can contain no ordinary particles while retaining space, time, quantum fields, laws, and measurable potential energy. In quantum theory, a vacuum is not inert blankness but the lowest energy arrangement of fields, capable of fluctuations and constrained by precise rules of nature. The phrase lowest energy can sound like complete stillness, but quantum mechanics does not permit every field to become perfectly motionless. Fields possess irreducible uncertainty, a consequence of the theory's basic structure, rather than a failure of measurement. Their measurable values can fluctuate around a minimum, leaving subtle effects that physicists can calculate and, in some circumstances, observe. The Casimir effect, for example, shows that closely spaced conducting plates can experience a tiny force related to altered quantum vacuum conditions. This is not a door through which reality materializes from literal nothing. It is evidence that even a vacuum has physical character. Those fluctuations do not mean particles simply emerge from philosophical nothing without conditions, causes, or mathematical structure already present. They describe changing quantities within a theory that assumes fields, a vacuum state, space-time, and equations governing nature. Popular descriptions sometimes call these events creation from nothing, because no ordinary particle existed beforehand in a particular location. Yet the quantum vacuum is an elaborately structured physical condition, not the absence of all conditions. Calling this nothing may be useful shorthand, but it changes the question before an answer begins at all. The distinction matters because the universe's origin is often introduced through pictures that smuggle in a surrounding emptiness. An explosion normally happens somewhere, at some time, within space that existed before the blast began to expand outward. Fireball imagery encourages us to imagine a central point surrounded by dark, waiting space. The Big Bang was not that kind of event, despite the powerful image suggested by its name today. The name itself was coined mockingly by astronomer Fred Hoyle during a 1949 radio broadcast, although the phrase endured. It describes the universe's early hot, dense condition and the rapid expansion of space from that condition forward. Galaxies are not debris racing through a pre-existing void from one central cosmic detonation point in space itself. Across vast distances, space expands, increasing separations between unbound galaxies without requiring an outside into which everything travels. A useful image is not shrapnel flying through air, but marks on a stretching surface, each mark seeing the others move away. The analogy has limits, because a balloon surface has an exterior and a center in a higher dimension. The universe need not possess either. Its value lies in showing how every location can observe recession without becoming the privileged center. The observable universe has no established center of expansion within its own geometry, because every sufficiently distant region sees other regions receding overall from its perspective. In the 1920s, observations of galaxy spectra revealed a systematic redshift, meaning their light had been stretched during its journey. Edwin Hubble's measurements helped show that more distant galaxies generally recede faster, a pattern expected in an expanding cosmos. Redshift does not mean galaxies are merely fading from view. It records the enlargement of the space through which their light travels, imprinting cosmic history onto the light itself. This is difficult because our minds evolved inside space, using locations, directions, and ordered temporal sequences for survival. When cosmology says space expanded, it challenges the instinct that expansion needs an already empty container around it. The earliest universe was not a small object placed inside a larger dark room waiting to receive it. It was a state in which distances, temperatures, densities, and physical interactions differed radically from those measured today. As expansion continued, the universe cooled, allowing later transitions that eventually produced particles, atoms, stars, planets, and observers. For its earliest accessible stages, the cosmos was more like an intensely hot, opaque plasma than the transparent star-filled scene visible today. That broad history is not speculation alone, because it leaves measurable signatures in the sky and matter today. But confirming an expanding early universe does not automatically reveal why anything existed, or whether existence truly began. Standard cosmology works extraordinarily well after the earliest fractions of a second that observations can meaningfully address directly. It explains cosmic expansion, primordial element abundances, the relic microwave background, and the growth of structure from early irregularities into galaxies across billions of years of evolution. These are not isolated clues. They form a connected account in which independent observations repeatedly point toward a younger universe that was hotter, denser, and more uniform. The microwave background is especially evocative. It is ancient radiation released when the cooling universe became transparent, roughly 380,000 years after its earliest hot phase began. Before then, light scattered constantly from charged particles, unable to cross long distances through the dense plasma. As electrons joined atomic nuclei, neutral atoms formed and light finally travelled freely across the cosmos. That cooled light now arrives as microwaves from every direction, carrying tiny temperature variations that later grew into galaxies and clusters. A map of those variations resembles a mottled celestial afterimage, a record from an epoch when no stars yet illuminated the dark. These successes make the model indispensable, yet they mark a boundary rather than a complete account of origins. At extreme densities and temperatures, our best separate theories of gravity and quantum physics no longer fit together. General relativity describes gravity and evolving space-time brilliantly on cosmic scales, while quantum theory governs microscopic behavior with extraordinary accuracy. Near the earliest conceivable moments, both descriptions should matter, but no confirmed quantum theory of gravity yet exists. This is not a minor missing detail. It is a gap precisely where our questions about beginnings become most demanding. Running equations backward can produce an apparent singularity, where density and curvature become mathematically unbounded in simplified models. In such calculations, known quantities approach values that no physical instrument could meaningfully measure. This does not prove nature reached an actual infinite point, nor that science has located creation itself there. Instead, it signals that familiar equations have been pushed beyond the domain where they can be trusted fully. A singularity may be less like a photographed event than a warning light on a map, marking territory where the map no longer describes the terrain. The Big Bang model therefore begins with an early describable state, not a confirmed statement of absolute beginning. The phrase "before the Big Bang" then becomes more treacherous than it first appears to us now. If time emerged with the universe, asking what happened earlier may resemble asking for a direction beyond the northernmost point on Earth. The question is not foolish, because it identifies the edge where ordinary language meets unfamiliar physics and fails. Before usually means an earlier time, but that meaning assumes time already exists as an ordered dimension there. If no temporal dimension existed independently, there may have been no earlier moment waiting behind cosmic history at all. That possibility does not settle origins, but it prevents us from importing chronology into a regime beyond experience. Some proposals seek a prior phase, a bounce, an eternal inflationary process, or a larger quantum framework beyond ours. A bounce model, for instance, imagines contraction preceding expansion, while other ideas explore whether our observable history belongs to a wider process. Others treat the earliest boundary as a limit where prior language loses clear physical reference entirely for us. None has achieved confirmation sufficient to turn a compelling possibility into settled knowledge about the universe's first condition. This uncertainty is not failure, but the honest frontier separating evidence, inference, mathematics, and philosophical interpretation for now. It also returns us to the word nothing, which becomes less clear the more carefully we examine it. Every candidate origin story seems to retain some foundation, whether laws, fields, a quantum state, geometry, logical possibility, or a framework permitting change to occur at all. Perhaps that persistence reflects a limitation of human thought, or perhaps it identifies a genuine fact. Explanation may always begin from some structure, however abstract and unfamiliar. A law without a universe is difficult to picture, yet laws may not be objects existing like stones. They may instead describe stable regularities that become meaningful only when physical reality exists. A quantum state may sound empty, yet it already supplies possibilities, relationships and rules for physical outcomes to unfold. Geometry may contain no matter, yet it provides extension, structure, and a framework for distinguishing one location from another. Mathematical possibility appears even more abstract, but it raises whether possibility itself counts as something in any meaningful sense. Each proposal may explain how one physical condition develops from another without reaching literal non-existence at its base. That is the tension beneath every confident claim that science has shown something can come from nothing alone. Science can test models when they generate consequences, but absolute nothing offers no obvious properties, conditions, or predictions. If it has no space, time, laws, fields, relations, or potential, what could science describe about it? There is no location to inspect, no duration to model, and no process from which a measurable consequence could arise. If it has properties permitting change, then it may no longer be nothing in the strict sense we seek. The central question may therefore divide into two enduring mysteries: why there is a universe, and whether absolute nothing could ever produce one by any means. Neither mystery yields easily to intuition, because intuition was trained by a world where things already exist around us. The task is not to force a comforting answer, but to identify precisely what each answer assumes first. That discipline turns a vague riddle into questions physics can sharpen, test, or recognize as currently unanswered problems. It also protects wonder from easy answers, which can sound satisfying, while quietly assuming the very thing they claim to explain. We now move from imagined absence toward the traces left by a universe that undeniably changed and expanded. Those traces cannot show an origin directly, but they can restrict which cosmic histories remain physically plausible today. Light arriving from distant galaxies records earlier conditions, carrying information across time within expanding space to our instruments. Telescopes are therefore not merely machines for seeing far away. They are instruments for looking backward, because light from remote objects has spent millions or billions of years crossing the intervening cosmos. The cosmic microwave background preserves radiation released when the young universe first became transparent to travelling light freely. Element abundances, galaxy patterns, gravitational waves, and particle experiments offer separate tests of early cosmic conditions and processes. Hydrogen and helium, for example, carry chemical evidence of nuclear reactions during the first minutes of cosmic history. The distribution of galaxies preserves the amplified imprint of minute early variations, while high-energy experiments test the behaviour of matter under conditions that echo the young universe. Together, these clues let cosmologists reconstruct increasingly early chapters without pretending they can observe a time before time. Evidence cannot yet deliver a photograph of nothing, but it can reveal where our successful theories begin, where they break, and what new explanations must confront next. That boundary is itself a profound discovery. The universe has left records of its transformation across radiation, matter, motion, and the geometry of space, even if its deepest beginning remains concealed. We have removed galaxies, stars, planets, particles, and darkness, only to discover that removal itself presumes a framework still. Now the evidence speaks, and the universe's surviving light carries us toward the earliest moment physics can reach. We begin not with imagined emptiness, but with surviving signals that describe the universe's measurable early transformation in detail. Light reaches Earth carrying records of distant places, earlier times, changing conditions, and the expansion between galaxies. Telescopes do more than look far away. They look backward through cosmic history because light requires time to arrive. Travel outward from the Milky Way, past neighbouring galaxies, clusters, and immense filaments connecting matter across intergalactic darkness. The farther telescopes reach, the younger the observed universe becomes, because ancient light has travelled longer distances toward us. Distant galaxies show a systematic redshift, with familiar spectral patterns shifted toward longer, redder wavelengths during their journeys. Redshift can arise from motion, but cosmic observations reveal something broader than countless galaxies independently fleeing our location. Spectroscopy gives this conclusion unusual force. Each element leaves a distinctive sequence of bright or dark lines when atoms and ions absorb or emit particular wavelengths. In remote galaxies, those same sequences arrive displaced together, as though light's ruler has been gently stretched. The farther a signal travels through expanding space, the greater its accumulated shift becomes. That measurable stretching lets astronomers translate colour into cosmic history. In the 1920s, Edwin Hubble compared galaxy distances with their redshifts and uncovered a striking large-scale relationship. Generally, more distant galaxies recede faster, producing what became known as Hubble's law and transforming modern cosmology permanently. The pattern does not mean Earth occupies a special central position from which every galaxy escapes into darkness. observers in sufficiently distant galaxies would see the same overall recession, with their own local region appearing comparatively central. Hubble's original measurements depended on Cepheid variable stars, pulsating beacons whose intrinsic brightness could be estimated. By comparing that known brightness with their faintness, astronomers inferred distances across nearby galaxies. The data were imperfect by modern standards, yet their implication was unmistakable. Later observations using supernovae and wider surveys confirmed the relation across far deeper volumes. A quiet graph of lines and distances had revealed a universe in motion. This is the signature of expanding space. On the larger scales, the distance between unbound galaxies increases as cosmic geometry evolves. Galaxies can move locally through space, pulled by gravity within groups and clusters, yet the broader expansion stretches separations. Our nearby Andromeda galaxy is approaching the Milky Way, demonstrating that expansion does not dictate every local motion everywhere. But beyond gravitationally bound systems, the expansion trend dominates, and redshift maps its accumulated effect across deep cosmic time. The familiar raisin bread analogy can help if its limits remain visible throughout the comparison. Imagine raisins embedded within rising dough. As the dough expands, every raisin sees other raisins become more distant. More distant raisins separate faster because more expanding dough lies between them, not because one raisin occupies the center. Galaxies resemble those raisins only in this limited sense. Space stretches between large-scale cosmic structures as the universe expands. The analogy fails if we imagine an outer edge, a bakery, or a central point beyond the bread. The universe need not expand into a surrounding emptiness, and observations reveal no center inside cosmic space itself. Expansion describes changing distances within space-time. It does not require galaxies to race through a pre-existing void from one explosion site. The Big Bang was not that kind of event. Despite the powerful image suggested by its name today, the name encourages a misleading picture of a tiny fireball detonating somewhere within an already existing dark arena. Cosmology instead describes an early condition shared across the region that later became our observable universe. Every sufficiently large region was hotter, denser, and more compressed than its later descendants, including the space between galaxies. There was no established outside from which to watch it expand, and no observed central location where it began. The expansion itself offers a powerful method for reconstructing the past. Measure today's cosmic growth, then reverse the equations governing how density, temperature, and distances change. Running that history backward makes average separation shrink, radiation grow hotter, and matter become increasingly dense. The result is not a miniature object sitting in an empty room. It is an earlier state of space itself. That reversal also explains why the night sky offers a kind of thermal archive. Radiation loses energy as space expands, so its temperature falls in a precisely calculable way. Matter becomes more dilute, while gravitational clumping slowly becomes more influential. By comparing these linked changes with present measurements, cosmologists test not merely a direction of history, but its changing physical conditions. This mathematical reversal does not mean cosmologists can replay every instant with equal confidence. Evidence becomes thinner as conditions grow more extreme, and familiar theories eventually encounter their limits. Yet the basic conclusion remains exceptionally well supported. Our observable cosmic history emerged from a much hotter, denser phase than the universe we inhabit today. Several independent relics preserve evidence of that phase, and each tests the same broad story differently. The first major relic surrounds us almost uniformly, although human eyes cannot see it directly. It is the cosmic microwave background, a faint bath of radiation arriving from every direction in space. This radiation is not starlight scattered through nearby dust. It is cooled light released by the young universe itself. Its existence was predicted before it was accidentally detected in 1965 by Arno Penzias and Robert Wilson. Before its discovery, the microwave background had already emerged from calculations by George Gamow, Ralph Alpha, and Robert Herman. They recognized that a hot early universe should leave cooled radiation behind, even after stars and galaxies transformed the sky. Penzias and Wilson encountered that prediction as stubborn radio noise, a uniform hiss that persisted despite every practical attempt to remove it. Their horn antenna, framed against the New Jersey sky, had detected a fossil signal without initially knowing its origin. Early cosmic matter was an intensely hot plasma of charged particles and photons continually scattering from one another. Electrons could not remain attached to atomic nuclei because energetic collisions repeatedly tore any new atoms apart. Light therefore could not travel freely across long distances. It was trapped in an opaque glowing fog where photons constantly changed direction. Expansion cooled this plasma over hundreds of thousands of years, changing the rules governing matter and radiation. About 380,000 years after the hot early phase began, electrons combined with protons to form neutral hydrogen atoms. Helium nuclei also captured electrons, leaving far fewer charged particles available to scatter passing photons. This transition is called recombination, though it was the first stable assembly of atoms in cosmic history. Once neutral atoms formed, the universe became transparent enough for light to travel freely across enormous distances. That released radiation has crossed expanding space ever since, cooling dramatically as its wavelength stretched. Today, that ancient light arrives as microwaves with a temperature only a few degrees above absolute zero. It provides a snapshot of the universe when no stars, planets, or galaxies yet illuminated the cosmic darkness. The microwave background is therefore an afterglow, not a picture of an absolute beginning. It shows a young, cooling universe already governed by physical processes that modern instruments can measure precisely. Its near uniformity reveals that the early cosmos was remarkably smooth on the largest observable scales. But it was never perfectly smooth. Tiny temperature variations mark slight differences in density across the primordial plasma. Those differences were extraordinarily small, yet gravity amplified them over billions of years. Slightly denser regions attracted more matter, eventually building galaxies, galaxy clusters, and the vast filamentary structure mapped by modern surveys. The mottled maps contain more than random texture. In the early plasma, gravity pulled matter inward, while radiation pressure pushed outward, creating vast sound waves through the hot fog. Their frozen pattern appears as subtle, angular features in the background. Like the resonant tones of an instrument, those features reveal the density, composition, and spatial geometry of the young cosmos. Such precision turns a faint microwave glow into a quantitative record of conditions billions of years before Earth existed. The detailed pattern of these variations became one of cosmology's most valuable records. NASA's COBE mission first detected the fluctuations clearly in 1992, confirming that the background contained subtle primordial structure. WMAP then measured their pattern with far greater precision, refining estimates of cosmic age, composition, and geometry. The European Space Agency's Planck mission sharpened the map further, testing the standard cosmological model with unprecedented detail. These missions did not observe galaxies being born directly. They measured initial conditions from which later structures could plausibly grow. Their results fit a universe dominated by ordinary matter, dark energy, radiation, and tiny early irregularities. The match between predicted patterns and observed patterns is a major success for modern cosmology. It does not answer why these ingredients exist, but it strongly constrains how our observable cosmos evolved. Another relic is written into matter itself, especially the universe's simplest chemical elements. During the first minutes, temperatures and densities allowed nuclear reactions unlike those inside later stars. Protons and neutrons combined to form mostly hydrogen and helium nuclei, with traces of deuterium and lithium. This brief era is called primordial nucleosynthesis. It occurred before atoms existed, when matter remained a hot plasma filled with energetic particles. The predicted proportions are remarkably specific. Big Bang theory expects roughly 3/4 hydrogen and 1/4 helium by mass, with minute amounts of other light elements. Observations of ancient gas clouds and primitive stars broadly confirm these primordial abundances. Stars later manufacture many heavier elements, but they cannot easily erase the early chemical fingerprint everywhere. Hydrogen, helium, deuterium, and lithium therefore provide an independent test of the hot early universe. Deuterium is especially revealing because stars tend to destroy it, rather than manufacture large new supplies. Consequently, measurements of pristine distant gas can preserve an unusually clean estimate of early cosmic conditions. Lithium presents a more complicated picture, with observed amounts differing from the simplest predictions in ways still debated. That tension does not overturn nucleosynthesis, but it reminds us that successful theories are refined through stubborn details, not protected from them. no single observation proves the whole cosmic account alone. Expansion, microwave radiation, light element abundances, and structure formation reinforce one another across radically different physical scales. Together they form a connected framework that explains more evidence than competing models have managed to explain. The Big Bang model earns its authority through these converging tests, not through a dramatic name or philosophical appeal. Its strength lies in prediction, measurement, correction, and repeated confrontation with the observable universe. To understand what this evidence supports, we can follow the compressed timeline it reconstructs. During the earliest fractions of a second, known physics describes conditions far hotter than any laboratory can reproduce completely. Energy dominated the scene, and particles interacted so rapidly that ordinary matter could not yet exist stably. As expansion continued, the universe cooled through a sequence of thresholds, each allowing new forms of matter and structure. These thresholds were not dramatic boundaries drawn across a cosmic clock. They were changes in what the cooling environment permitted, as temperatures fell below energies required to sustain earlier particle states. The chronology is therefore a history of phase transitions, confinement, and decoupling. Each transformation altered what could travel freely, what could bind together, and what future structures could inherit. In this sense, the young universe was not simply expanding. It was repeatedly becoming a different physical place. At extremely early times, quarks and gluons formed a dense hot plasma, rather than the protons and neutrons familiar today. Quarks are fundamental constituents of matter, while gluons carry the strong force binding quarks together. Under those immense temperatures, they moved in a collective state unlike atoms, nuclei, or later ordinary matter. Experiments using particle colliders have recreated brief quark-gluon plasma conditions, helping physicists test aspects of this ancient regime. As cooling proceeded, quarks became confined inside composite particles, including protons and neutrons. Matter and antimatter were produced in enormous numbers, often annihilating back into radiation when they encountered each other. Yet some tiny imbalance favoured matter over antimatter. For reasons still not fully understood, roughly one extra matter particle survived for vast numbers of annihilating pairs. Those survivors became the material basis for nuclei, atoms, stars, planets, and living observers. This matter-antimatter asymmetry remains an unresolved clue, not a finished explanation of cosmic origins. Known particle physics contains possible mechanisms, but observations demand conditions that remain under active investigation. Without that slight imbalance, nearly all matter would have annihilated, leaving a universe filled mainly with radiation. The existence of ordinary matter therefore records a decisive early process whose complete cause science has not established. Within the first minutes, protons and neutrons formed the light nuclei predicted by primordial nucleosynthesis. Then expansion cooled the universe too much for widespread fusion to continue efficiently. For hundreds of thousands of years afterward, nuclei and electrons remained separate inside the opaque plasma. Atoms formed only after recombination, when cooling finally permitted electrons to remain bound to nuclei. The released microwave background marks the transition between an opaque plasma and a transparent cosmic environment. After recombination came the cosmic dark ages. Neutral hydrogen filled space, while no stars yet burned to illuminate it. Gravity gradually drew matter into denser regions, guided especially by the gravitational pull of invisible dark matter. Dark matter does not emit light in the usual way, but its gravity strongly influences galaxy formation and cosmic structure. Over time, the first stars ignited inside growing clouds, ending the darkness with ultraviolet light and nuclear fusion. Because dark matter interacts weakly with light, astronomers infer its presence through gravitational effects rather than direct images. It formed invisible gravitational scaffolding before ordinary gas could cool efficiently, deepening the wells where the first luminous objects would arise. When those stars ignited, their radiation did more than brighten the darkness. It altered the state of intergalactic hydrogen, making the universe progressively transparent to ultraviolet light and reshaping the signals later telescopes seek. Those first stars transformed their surroundings, heating and ionizing much of the neutral hydrogen between galaxies. Later generations forged heavier elements, spreading carbon, oxygen, iron, and other materials through stellar winds and explosions. Galaxies assembled, merged, and evolved. Planetary systems eventually formed around later stars enriched by earlier stellar deaths. The universe became capable of chemistry, complexity, memory, and questions about its own history. This timeline is profound because it turns distant observations into a testable narrative of cosmic change. But its beginning must be described carefully. The evidence strongly supports a hot, dense, expanding early phase. It does not directly show literal nothing transforming into something. No telescope observes an absence of space, time, fields, laws, or physical possibility. The Big Bang model traces the evolution of an early universe. It does not, by itself, establish the ultimate origin of all reality. That distinction is often lost when the phrase beginning of the universe is used without qualification. In ordinary language, a beginning suggests a first moment preceded by nothing at all. In cosmology, the phrase may instead identify the earliest phase our successful equations can reconstruct. These meanings overlap only if evidence shows that time, space, matter, energy, and laws all emerged from absolute non-existence. Current observations do not demonstrate that stronger claim. We now move from imagined absence toward the traces left by a universe that undeniably changed and expanded. Those traces lead backward with remarkable power, but they eventually approach a frontier where present theories lose reliability. General relativity describes gravity as the geometry of spacetime, and it predicts cosmic expansion with extraordinary success. Quantum theory describes particles, fields, and microscopic uncertainty with equally impressive precision under very different conditions. Near the earliest conceivable moments, both theories should matter simultaneously, yet they remain incompletely unified. When cosmologists extrapolate classical general relativity backward, density and spacetime curvature can rise without limit. Mathematical models approach a singularity, where familiar quantities become infinite and ordinary descriptions appear to break down. This result has enormous historical importance, but it should not be mistaken for a photographed cosmic event. An infinity in an equation often signals that a theory is being applied beyond its proper domain. It may reveal a boundary in knowledge rather than an actual physical point of infinite density. The word singularity can sound like a destination, a pinpoint at the start of a cosmic film. Mathematically, however, it marks where the film projector fails. General relativity treats spacetime as smooth, an approximation tested magnificently at accessible scales, but quantum effects should dominate near the Planck scale. There, geometry itself may fluctuate. Any confident picture of a literal first instant would therefore exceed what current equations can responsibly supply. Consider other moments in science when infinities exposed incomplete descriptions rather than literal features of nature. Classical physics once predicted impossible behavior for hot objects, until quantum theory replaced the failing assumptions. Singularities may similarly indicate that general relativity requires quantum corrections at extreme densities and tiny scales. A complete quantum theory of gravity could alter the backward extrapolation, perhaps replacing the singularity with another physical process. No confirmed theory yet tells us exactly what happens there. This is the singularity problem. The equations suggest a limit, but the physical meaning of that limit remains unresolved. Did the universe pass through a quantum state? Did a prior phase contract before rebounding? Did time itself begin, making earlier questions physically undefined? Could our observable region emerge from a larger process that continues beyond our horizon? These remain proposals, not established conclusions supported by decisive observational evidence. The absence of certainty does not weaken the evidence for the hot Big Bang phase. It clarifies exactly what the evidence reaches and where inference becomes more speculative. We can measure expansion, ancient radiation, light elements, and primordial fluctuations with extraordinary accuracy. We cannot yet measure a literal transition from absolute nothing into the first physical reality. The difference between those statements is the difference between a tested history and an ultimate metaphysical claim. Some popular accounts say quantum physics proves that something can come from nothing. Usually, however, their nothing is a quantum vacuum, a field state, or a law-governed physical framework. Such states can contain fluctuations, energy, relationships, probabilities, and rules that determine what may occur. They are not the absolute nothing considered in our opening question. Calling them nothing can obscure the very distinction the origin question requires us to examine. A quantum vacuum may contain no ordinary particles at a particular moment, yet it remains physically structured. It presumes quantum fields, a state space, mathematical laws, and often space-time itself. Fluctuations within that vacuum are not events arising without any conditions whatsoever. They are consequences of a theory whose basic ingredients have already been assumed. This does not make quantum cosmology unimportant. It makes precise language essential when discussing what such models actually explain. The same caution applies to proposals involving inflation, tunneling, eternal cosmology, or multiverses. Some models attempt to describe how an expanding universe could emerge from a prior quantum condition. Others suggest our visible universe is one region within a vastly larger cosmic process. These ideas may generate testable consequences and deserve serious investigation, but none has demonstrated that absolute philosophical nothing produced everything without any prior structure, law, or possibility. The word nothing carries different meanings in ordinary speech, physics, and philosophy. In ordinary speech, it may mean an empty room, an unoccupied region, or the absence of an expected object. In physics, it may mean a vacuum state with no particles of a certain type. In philosophy, absolute nothing means no objects, no properties, no space, no time, no laws, and no possibilities. Confusing these meanings allows apparent answers to solve easier questions than the deepest one asks. The evidence of cosmology cannot simply be dismissed because it does not answer every version of nothing. Its achievements are real and astonishing. It tells us that the observable universe evolved through a hot, dense, expanding early phase. It identifies when light escaped, when nuclei formed, when structures began growing, and how later cosmic complexity developed. It gives a history extending far beyond human intuition, grounded in signals measured across the sky. But science advances by identifying boundaries as clearly as it identifies successful explanations. A theory earns trust by stating where it applies, what it predicts, and what observations could challenge it. The Big Bang framework does not say everything began from literal nothing. It says our observable universe has a traceable history leading back toward conditions of extraordinary heat and density. Beyond a certain frontier, new physics may be required before further questions become scientifically answerable. This frontier is not empty ignorance. It is a structured problem defined by evidence, equations, and the mismatch between gravity and quantum mechanics. Physicists can ask whether early fluctuations left detectable signatures in the microwave background. They can test particle interactions relevant to matter-antimatter asymmetry. They can search for primordial gravitational waves or departures from standard cosmological predictions. Each result narrows the range of viable stories about the earliest accessible universe. Yet the ultimate question remains difficult because causation itself may depend on time. We normally ask what caused an event by placing a cause earlier than its effect. If time emerged with the cosmic history we observe, there may be no earlier temporal arena containing a cause. That possibility does not prove that the universe came from nothing. It shows that ordinary causal language may fail at the boundary we're trying to describe. Likewise, asking where the Big Bang happened assumes a space in which locations already exist. But if space itself was evolving from an earlier extreme state, there may be no external coordinate system available. Cosmology does not replace mystery with nonsense. It replaces misleading pictures with more precise questions about what our concepts can legitimately describe. The more carefully we define nothing before, cause, and beginning, the more demanding the central question becomes. The microwave background offers a useful reminder of this discipline. It is ancient, but not infinitely ancient. It comes from 380,000 years after the early hot phase began, not from a moment of creation. Its photons tell us about recombination, density variations, and cosmic geometry, not about an absolute absence preceding existence. The farther back we reconstruct, the less direct our evidence becomes. At the deepest boundary, mathematics must be joined by caution, humility, and new experimental imagination. The story of cosmic expansion therefore contains two truths that must remain together. First, the Big Bang model is among the strongest and most successful frameworks in all science. Second, its success does not settle whether there was ever literal nothing or why reality exists at all. Removing the second truth turns evidence into mythology. Removing the first turns genuine scientific discovery into unnecessary doubt. Our next step leads beneath the smooth grandeur of expanding space toward the smallest scales imaginable. There, particles become excitations of fields, certainty becomes probability, and empty space reveals unexpected structure. The apparent cosmic stage begins to dissolve into quantum uncertainty. In that unfamiliar domain, popular claims about something arising from nothing will sound more plausible. They will also require closer inspection, because quantum nothing may still be very far from no thing whatsoever. The echo of creation is real. It reaches us as red-shifted galaxies, ancient microwaves, light elements, and structures grown from minute primordial variations. These records tell a coherent story of change from a hotter, denser early universe toward the vast cosmos visible today. But an echo is not the original sound. It carries evidence of what followed, while leaving the deepest source partly concealed beyond the present reach of science. That concealed boundary is where the word nothing returns with greater force. Did the universe really begin from nothing, or does every proposed beginning retain some underlying physical or conceptual foundation? Modern cosmology has not closed that question. Instead, it has made the question sharper by revealing how much structure already exists within every serious model. To approach the answer, we must now enter the quantum world, where emptiness is never as simple as it first appears. The next chapter examines that world carefully, separating observed quantum behavior from the metaphors used to describe it. It asks what fields are, what vacuum states contain, and why fluctuations do not automatically explain existence itself. The cosmic evidence has carried us near the earliest accessible horizon. Beyond it, the smooth stage of space-time begins to break apart. There, uncertainty becomes fundamental, and the mystery of nothing changes shape again. Previous chapters carried us backward through expanding history, toward conditions where classical gravity and quantum physics must meet. Now the investigation narrows from cosmic evidence to the empty foundation beneath every particle and force. Quantum theory does not reveal a blank arena behind the universe. It reveals structure without particles. Quantum field theory begins with a reversal of everyday intuition. Particles are not treated as independent tiny objects moving through an otherwise passive space. They are excitations of fields that extend throughout space-time. An electron is an excitation of the electron field. A photon is an excitation of electromagnetic fields. In this view, the familiar particle is more like a localized pattern in an underlying medium of possibilities, although the analogy has limits. A wave on water requires water molecules, while a quantum field is not assumed to be made from some simpler material. It is part of the basic inventory of the theory. Wherever the electron field exists, an electron-like excitation can, under the right conditions, appear. The visual contrast is striking. Classical intuition pictures a dark, silent chamber, awaiting objects that enter from outside. Quantum field theory replaces that chamber with overlapping, invisible presences extending through every volume of space. The room may contain no detectable particles, yet the fields remain, poised within their lowest allowed condition. Fields are not material fluids spread like mist, although that image can guide intuition. They are fundamental quantum systems described by values and relationships at every location where the theory applies. Their allowed excitations carry properties, including mass, charge, momentum, and spin. What we call matter is organized field activity. This idea emerged gradually during the 20th century, when physicists tried to unite quantum mechanics with Einstein's special relativity. Ordinary quantum mechanics could describe atoms with remarkable precision, but relativity allowed particles to be created and destroyed. Quantum field theory made that possibility natural. Fields became primary, while particles became countable events within them. The distinction matters because particles of the same kind are perfectly identical. Every electron has the same mass, charge, and spin, regardless of where it is found. Field theory explains that sameness elegantly. Each electron is an excitation of one universal electron field. The cosmos does not manufacture separate electron blueprints. It expresses one underlying field in repeated, measurable forms. This framework changes what an empty region means. A detector may find no particles within a chosen volume, yet the relevant fields still exist there. They retain possible states, correlations, and equations governing their behavior. Empty space is therefore not necessarily featureless space. It is a physical condition of fields. A particle detector does not simply observe everything that exists. It responds when a field transfers energy, momentum, or charge in a manner the instrument can register. Silence from the detector means that no appropriate excitation was recorded. It does not mean the apparatus has peered into literal non-being. That difference will shape every claim that follows. The quantum vacuum is the lowest energy state available to a set of fields under specified conditions. Lowest energy does not mean no energy, no motion, or no structure exists. It means no lower state can be reached without changing the system or its constraints. The vacuum remains a state, not an absence. Even that phrase, lowest energy, demands care. Energy is defined relative to a physical description, and different arrangements can alter what the lowest state looks like. Put fields in a metal cavity near a surface or within curved space-time, and the permitted modes may change. The vacuum is never merely a universal blackness behind all theories. It presupposes quantum fields, mathematical rules, permitted observables, and usually a space-time setting in which those fields are defined. It may also depend on boundary conditions, symmetries, and a choice of what counts as energy. Calling this elaborate arrangement, nothing risks replacing one question with a less demanding word entirely. A true absence of particles can still be exceptionally rich in formal structure. Equations determine which disturbances are possible. Symmetries constrain which quantities remain conserved. Boundary conditions specify what fields may do at edges or surfaces. The vacuum is quiet only in the limited sense that it contains no ordinary particles above its ground state. This distinction matters because popular accounts often invoke a vacuum when they claim the universe emerged from nothing. They may mean no particles existed in some prior state, but a particle-free state is still a physical state with possibilities already encoded within it. The question asks whether anything preceded everything. At quantum scales, uncertainty is not merely ignorance caused by imperfect instruments or incomplete information. Quantum mechanics places structural limits on the simultaneous precision with which certain paired quantities can be specified. Position and momentum provide the familiar example. Field values and their conjugate rates of change obey analogous limits. The limitation arises from the mathematical architecture of quantum theory. Certain observables are represented by operations that do not commute, meaning their order matters in a fundamental way. A state can be sharply defined for one member of such a pair, but not arbitrarily sharp for both. Nature is not hiding complete classical details behind a curtain. This is why a quantum field cannot generally settle into the perfectly motionless condition imagined by classical physics. Attempting to pin its value exactly would make the corresponding rate of change maximally indeterminate. The ground state instead contains an irreducible spread in possible measurement outcomes. That spread is not a mechanical jitter of tiny hidden beads. The uncertainty principle does not say that any quantity may violate conservation laws for a brief interval. Energy remains rigorously conserved in a properly defined closed system, whose governing laws do not explicitly vary with time. The principle instead says that a quantum state cannot assign infinitely sharp compatible values. A common slogan invokes an energy-time uncertainty relation, then imagines nature permitting temporary debts. Yet time in quantum theory does not usually function as an ordinary observable, paired with energy in the same way position pairs with momentum. The slogan can obscure more than it reveals. Conservation laws remain embedded in the symmetries of the physical description. That irreducible spread means the lowest energy state generally retains fluctuations in measurable field quantities, rather than becoming a perfectly silent classical configuration. These fluctuations are features of a state governed by quantum rules. They do not license unlimited creation, erase debts, or violations of conservation principles within nature's framework already. The word fluctuation can also mislead when treated as a miniature event unfolding like a movie. Often it refers to the statistical range of results found when equivalent measurements are repeated. Correlations between measurements may reveal this structure with extraordinary precision. What fluctuates is defined by the theory and the experiment, not by a vague permission for anything whatsoever. Metaphors about particles borrowing energy from the vacuum and repaying it before discovery are memorable but misleading. They confuse uncertainty relations with temporary permission to break conservation. In quantum field theory, calculations track energy, momentum, charge, and other conserved quantities with exacting discipline. The vacuum is not a credit account, yet quantum fields can produce effects that look startling when compared with classical emptiness. Their ground states possess correlations and fluctuations that influence measurements under carefully controlled conditions. Physicists do not infer this activity from metaphor alone. They calculate consequences and compare them against experiments that can distinguish competing explanations. One famous case is the Casimir effect, observed when closely spaced conducting surfaces experience a small force. Quantum field calculations predict that boundaries alter the allowed electromagnetic modes between and outside the plates. The resulting difference can produce an attractive force. Measurements agree with this broad prediction under demanding laboratory conditions. Imagine two polished metallic plates facing one another across a gap thinner than a human hair, separated by distances measured in nanometers or micrometers. At such scales, the force is faint but detectable. Precision instruments must account for surface roughness, electrical properties, temperature, and stray charges. The experiment is less like a magic trick than a demanding interrogation of nature. The original calculation, developed by Hendrik Casimir in 1948, gave physicists a memorable way to connect abstract field modes with a measurable force. Conducting boundaries restrict which electromagnetic patterns can fit between them. Outside, a different set of modes remains available. The imbalance changes the energy associated with the configuration, and the plates respond. Popular images portray the Casimir effect as fewer virtual particles fitting between plates than outside them. That picture can organize a calculation, but it is not the only interpretation. The effect can also be described through changes in electromagnetic field modes and material interactions. It does not photograph particles escaping. Indeed, real materials are crucial to accurate predictions. A perfect conductor is an idealization, while actual metal responds to electromagnetic fields through its electrons and atomic structure. Different calculational approaches can emphasize vacuum modes, induced charges, or electromagnetic response. They converge on observable forces, reminding us that a successful image is not always a literal ontology. The experiment demonstrates that a vacuum subject to boundaries has measurable physical consequences. It does not demonstrate that literal nothing manufactures matter without conditions. Conducting plates, electromagnetic fields, quantum electrodynamics, laboratory geometry, and procedures are all already present. The effect deepens the mystery of vacuum structure rather than dissolving it. Spontaneous emission provides another window into vacuum physics. An excited atom can release a photon even when no incoming light triggers the transition. Quantum theory relates the emission rate to the atom's coupling with electromagnetic field modes available around it. The vacuum helps define those possibilities and influences observable decay. An atom in an excited state resembles a tightly wound physical arrangement, not a particle appearing from nowhere. Its electrons occupy quantized energy levels, and a transition to a lower level releases a definite energy difference. That energy can emerge as a photon with an appropriate frequency. The field supplies available channels while the atom supplies the energy. The environment can alter the process dramatically. Place an atom in a carefully engineered cavity, and some electromagnetic modes become enhanced while others are suppressed. Its emission rate can change accordingly. This phenomenon, often called cavity quantum electrodynamics, makes the vacuum's role experimentally tangible without transforming it into philosophical nothingness. Still, saying that the vacuum causes spontaneous emission can conceal important details. The atom begins in an excited state, carrying energy that the emitted photon can carry away. The surrounding field determines how the transition occurs and which modes receive it. Nothing here requires energy to arise from absolute non-existence itself. Virtual particles enter this story most often as lines inside diagrams used to organize quantum calculations. These internal terms represent mathematical contributions to interaction amplitudes, not directly observed miniature entities following ordinary trajectories through space. Different valid calculational descriptions can assign different virtual pictures to the same measurable result outside. The diagrams, introduced in their famous modern form by Richard Feynman, became powerful visual shorthand for interactions. Lines meet, split, and reconnect across a page, suggesting an unseen drama beneath every collision. But the drawing is not a camera frame. It represents terms in a calculation, including intermediate contributions that cannot be isolated as direct observations. Virtual particles are often called off-shell because they need not obey the same energy-momentum relation that applies to freely observed particles. That technical phrase does not make them lawbreakers. The complete interaction respects conservation laws at every vertex and in the final measurable result. The intermediate language belongs to a calculational framework, not ordinary cinematic reality. They are extraordinarily useful because they help physicists compute scattering outcomes, forces, radiative corrections, and atomic behavior. But usefulness does not turn every diagram into a literal microscopic movie. A virtual particle is not a tiny spark conclusively observed, appearing and vanishing from empty space. It is part of formalism. Real particles can certainly be created in physical processes, but those processes require specific conditions and conserve relevant quantities. High-energy collisions convert kinetic energy into new particle masses. Strong electric fields can produce particle pairs through carefully described mechanisms. Curved spacetime or accelerated motion can alter what observers call particles. At a particle collider, protons or electrons are accelerated until their kinetic energy becomes enormous on subatomic scales. When they collide, that energy can become mass, according to Einstein's familiar relation between mass and energy. Detectors then reconstruct tracks, sprays of particles, and decays from the collision debris. Creation is real, but the energy ledger is never empty. In sufficiently intense electric fields, theory predicts pair production through the Schwinger effect. The field performs work, separating oppositely charged particles and supplying the energy required for their masses. This is a remarkable prediction about quantum electrodynamics under extreme conditions. It is not an example of objects arising without fields, apparatus, or physical law. These phenomena are profound, yet none begins with philosophical nothingness. Colliders contain beams, detectors, fields, and energy. Strong field experiments contain apparatus and externally supplied work. Effects near black holes or accelerating observers presuppose quantum fields and spacetime geometry. The vocabulary of particle creation names transformations within structured reality already there. Even its lowest state can possess vacuum energy, a baseline contribution associated with quantum fields. In non-gravitational experiments, physicists often measure energy differences rather than an absolute zero. Gravity complicates that convenience because energy density can affect spacetime curvature and cosmic expansion. The vacuum may therefore matter cosmologically as well. This is where the smaller scales meet the largest. A uniform energy density does not dilute in the same way as matter when space expands. As the universe grows, matter spreads out, and radiation redshifts. A cosmological vacuum component remains approximately constant per unit volume, so its influence can eventually dominate the cosmic future. Einstein's equations permit a cosmological constant, a term that behaves like a uniform energy density permeating space. Observations indicate that cosmic expansion is accelerating at late times, consistent with a component often called dark energy. A cosmological constant remains the simplest successful description, though its microscopic origin remains uncertain today. The observational story began with distant supernovae in the late 20th century. These exploding stars served as cosmic distance markers, revealing that expansion was not slowing as expected under gravity alone. Later measurements of the cosmic microwave background and large-scale structure strengthened the picture. Something smooth and pervasive appears to influence the universe on its grandest scales. This connection makes vacuum energy both powerful and troubling. Straightforward quantum field estimates can yield values vastly larger than the observed cosmic energy density. The mismatches among physics unsolved problems. We can measure the acceleration and model its effects. We do not know why the vacuum's contribution is small. The discrepancy is not a minor numerical inconvenience. Depending on how one estimates high-energy contributions, the predicted value can exceed observation by an astonishing number of orders of magnitude. Physicists may suspect cancellations, undiscovered symmetries, or a deeper account of gravity and quantum fields. At present, none provides a confirmed explanation. That discrepancy should restrain easy claims that quantum vacuum energy explains everything. A quantity whose observed value remains mysterious cannot yet serve as a completed origin story. Vacuum energy may be central to cosmology, but its status underscores how incomplete our understanding remains. The vacuum is active, measurable, and unexplained. Some writers summarize cosmic origins by calling the universe a free lunch. The phrase captures an intriguing possibility from gravitation. Matter, radiation, and other positive energy contributions might be balanced by negative gravitational energy. If a total balance was zero, creation might seem less costly in intuitive bookkeeping terms alone. The expression became popular because it offers a provocative image. A universe rich with galaxies, stars, and life might nevertheless have a net energy that vanishes under a suitable accounting. It invites a tempting question. Could an immense cosmos emerge without requiring positive energy from elsewhere? Yet the mathematics behind that question is far less casual than the phrase suggests. The phrase is suggestive, not a settled theorem that the entire universe literally required no explanation. In general relativity, gravitational energy cannot always be defined as a simple local substance with one universal density. Space-time geometry is dynamic, and the accounting depends on symmetries, boundaries, and global assumptions being made. For an expanding universe like ours, defining total cosmic energy is technically difficult and may not yield one unambiguous answer. Conserved total energy is clearest in spacetimes with a suitable time translation symmetry. An evolving, expanding cosmos generally lacks that simple global symmetry. The free lunch remains an idea requiring caution. Even if some formulation shows zero total energy, a question appears. What establishes the fields, geometry, and laws that make such a balance meaningful? Zero is a relation between defined quantities, not the absence of quantities. A balanced equation may describe an origin process. It does not explain why equations exist. Here the discussion reaches a boundary between physics and philosophy, though the boundary is not a wall. Physics can test models containing laws and states by deriving observable consequences. It can compare rival accounts of inflation, fields, or cosmic evolution. But experiments do not test an absence of all conditions. Why do laws exist is not easily answered by writing more laws into a model. A law may be a timeless ingredient, a mathematical necessity, an emergent regularity, or a description of deeper structures. Each possibility changes the question. None automatically turns laws into literal nothing. The mystery may move downward. If laws are timeless ingredients, then they belong to whatever fundamental reality precedes our observable history. If laws emerge, we must ask from what underlying process or structure they emerge. If laws are descriptions rather than causes, we must ask what reality makes their regularities true. Every answer retains a foundation. Perhaps the demand for an explanation of laws misuses a concept built for events within time. Or perhaps it identifies an unanswered problem about why any stable order exists. Science need not decide that question prematurely. It can expose which assumptions are physical, which are mathematical, and which are philosophical. This restraint is not a failure of imagination. It is intellectual precision. A theory becomes more powerful when its starting assumptions are visible, because other theories can challenge, refine, or replace them. Concealing assumptions beneath the word nothing does the opposite. It makes a profound question sound solved before the work has begun. Quantum theory gives these questions sharper form because it makes probability fundamental without making every outcome arbitrary. A quantum state specifies a range of possible results and probabilities for them. It is not equivalent to no state at all. Indeterminacy within a framework differs completely from the absence of framework. A vacuum fluctuation is likewise not a spontaneous exemption from explanation. It is a change or uncertainty in field quantities described by a theory. The theory identifies what can fluctuate, how quantities relate, and what observations may reveal. Calling that process something from nothing uses nothing in a specialized, weakened sense. That does not make the quantum vacuum trivial or familiar. It remains one of nature's strangest experimentally grounded concepts. It contains no ordinary particles in its lowest state, yet it supports correlations, fluctuations, response to boundaries, and interactions with matter. Its emptiness is a precise physical achievement, not absolute absence. The vacuum depends on perspective in ways that challenge simple language. In curved spacetime or for accelerated observers, different definitions of particles can become relevant. Effects such as Hawking radiation and the Unruh effect show that particle descriptions can depend on geometry and motion. Fields remain deeper than particle pictures. For an observer falling freely toward a black hole, the local environment may look very different from the view of a distant observer watching from safety. For an accelerated observer, a state called empty by an inertial observer can appear to contain thermal particles. The lesson is not that reality is arbitrary. It is that particle language depends on how observers move through spacetime. These effects do not prove that particles are imaginary or that reality is observer-created. They show that particle number is not always the most fundamental description. Quantum fields, states, and space-time geometry organize predictions more reliably. The lesson is caution. An empty region may have different descriptions for different observers. At this point, the vacuum appears less like nothing than a prepared stage. But even stage is too passive an image. The vacuum participates in interactions, responds to conditions, and helps determine which phenomena occur. Still, it does not stand alone. Its definition normally assumes space-time in which fields exist. That assumption returns us to the origin question with greater precision. Can a quantum vacuum explain the universe if it requires a prior arena of space, time, fields, and laws? It may explain transitions from one physical state to another. It does not automatically explain the existence of the arena. Some cosmological proposals attempt to treat the vacuum itself as a beginning condition for a universe. They use quantum mechanics to calculate tunneling, nucleation, or transitions into expanding states. Such models may be mathematically coherent and testable in limited ways, yet their starting points still contain formal structures and possibilities. In such models, the word beginning may mean the earliest state described by a particular theory, rather than the absolute beginning of every condition. This distinction is easy to lose when equations are translated into dramatic language. A model might replace a classical singularity with a quantum transition. It has still assumed a rule for transitions in a space of allowed states. A model can be valuable without being an answer to every metaphysical question. Its value depends on whether it clarifies assumptions, yields predictions, and survives evidence. A quantum origin model may illuminate how a cosmos could develop from a state. It cannot by wording alone turn that state into nothing. The distinction is not wordplay. It determines what a theory has explained. If the starting point contains laws, then the theory explains consequences under laws. If it contains a quantum state, it explains evolution or probabilities from that state. The question concerns the starting ingredients themselves. That question remains open. Nor should philosophical nothingness be treated as a physical substance waiting to perform an action. If it had a tendency, a law, or a potential to produce universes, it would possess structure. If it stood through time before acting, time would already exist. Absolute nothing cannot function as a mechanism. This does not require surrendering the search for deeper explanations. It requires distinguishing a productive physical question from an undefined one. We can ask whether quantum gravity replaces singularities with calculable states. We can ask whether early fluctuations left observable signatures. We should not pretend that vocabulary alone eliminates mystery. The next challenge is gravity, because general relativity refuses to treat spacetime as a fixed container. Matter and energy shape geometry, while geometry guides matter and light. A vacuum defined on a given spacetime may become inadequate when spacetime itself must fluctuate quantum mechanically. The stage enters the drama as well. Einstein's insight transformed gravity from a force acting across a passive backdrop into the curvature of spacetime itself. Planets follow the contours of geometry. Light bends around massive objects. Clocks tick differently in stronger gravitational fields. If the geometry changes, then the very notions of distance, duration, and empty location become physically entangled with the contents of the universe. Near the Planck scale, familiar distinctions between fields, particles, distance, and duration may fail. Quantum gravity suggests that geometry could be unstable, granular, or emergent from deeper ingredients. No confirmed theory yet establishes which picture is correct. But every serious approach challenges the assumption that vacuum rests upon a background. The Planck scale lies unimaginably far beyond direct laboratory reach, where lengths are roughly 10 to the minus 35 meters, and conventional concepts may lose their reliability. At that frontier, quantum fluctuations of geometry could become as important as fluctuations of fields. Space may no longer resemble a smooth continuum. The map itself may become uncertain. If spacetime is quantum and dynamic, then asking what exists in an empty region may already assume too much. A region requires geometry. A vacuum requires fields and a definition of state. A before requires time. Gravity may force these concepts to emerge together rather than serving as starting points. Picture the familiar grid of space beginning to ripple, fragment and dissolve beneath the fields drawn across it. The distinction between stage and actor fades. what seemed like an empty container becomes part of the physical mystery. Perhaps the deepest question is not what appeared inside space, but how space, fields, and time became meaningful together. The mystery, therefore, does not disappear inside quantum physics, it becomes more disciplined. We learn that ordinary emptiness contains fields, that vacuum fluctuations are real within theory, and that measurable effects confirm vacuum structure. We also learn that this structure is something, however unfamiliar its properties may be to us. The vacuum refuses to be empty because nature refuses our simplest picture of emptiness. Behind a silent detector lies a web of fields, symmetries, possible measurements, and perhaps an energy that shapes the cosmic future. Yet every layer of explanation also reveals its own assumptions. The deeper we look, the more carefully we must define nothing. The question remains: previous chapter showed that the quantum vacuum is structured, not absolute nothing, and gravity now forces us to question the stage itself. Einstein's general relativity begins with a radical claim. Space and time are physical participants, rather than passive containers. Matter and energy tell spacetime how to curve, while curved spacetime tells matter, radiation, and clocks how to move. Gravity is therefore not simply a force operating inside a fixed cosmic arena with an independent universal clock. In the familiar image of relativity, a heavy star dimples a flexible grid, guiding planets along curved paths. The image is imperfect, yet it captures a crucial reversal in scientific thought. Geometry is not merely where events occur. Geometry helps determine which events can occur. Space can stretch, geometry can bend, and time can pass differently depending upon motion, gravity, and the evolving universe. A clock on a mountain ticks slightly faster than one at sea level, while a clock travelling rapidly ticks differently from one left behind. These effects are not philosophical curiosities. Satellite navigation systems must account for them, or their positions would drift by kilometres each day. The universe contains no single master clock, silently measuring every event from beyond the cosmos. Instead, time is registered locally by physical processes, atomic vibrations, radioactive decay, orbiting pulsars, chemical reactions, and the steady beating of living hearts. Each clock follows its own path through space-time, called its world line. This framework explains planetary orbits, gravitational lensing, black holes, and cosmic expansion with extraordinary precision across enormous physical scales. Light from distant galaxies can arc around intervening matter, forming luminous rings and distorted celestial images. Near black holes, clocks appear to slow relative to distant observers, while escaping light loses energy and reddens. Across the largest distances, space-time itself expands, carrying galaxies apart without requiring them to fly through a pre-existing outer void. It also changes the meaning of any question about what happened before the Big Bang. Before normally identifies an earlier location on a timeline already assumed to exist independently of the event being discussed. We use it without effort in ordinary life. Before sunrise, darkness covered the street. Before a star explodes, nuclear fuel changes within its core. Before a decision, competing possibilities seemed open. Human experience is organized through this sequence of earlier and later. But relativity treats time as part of space-time, linked to matter, energy, gravity, and cosmic history itself. If space-time has a beginning, then time may not provide an external sequence in which that beginning occurred. The phrase "before the beginning" may conceal an assumption that the beginning was an event inside a larger temporal container. General relativity gives us no automatic reason to assume that such a container exists. The question sounds simple, because human experience is organized through causes arriving before their visible effects. Every ordinary event occupies a temporal order, from falling stones to stellar explosions, births, deaths, and human decisions. We naturally seek the earlier condition that produced the later condition, then call that condition its cause. This habit is immensely successful within the universe. It helps scientists reconstruct earthquakes, trace epidemics, calculate planetary trajectories, and infer the lives of vanished stars. Yet the habit may become unreliable when the subject is the origin of temporal order itself. General relativity does not prove that time began, but it removes any automatic right to assume it existed forever. In Einstein's universe, a clock does not tick outside reality, while the cosmos unfolds beneath its indifferent measurement. A clock is a physical system within space-time, affected by velocity, gravity, and changing conditions around it. Time is not an empty corridor extending beyond all events in the straightforward manner everyday language suggests. It is woven into the physical relations that allow events to be ordered at all. This distinction becomes crucial when cosmologists reverse expansion toward denser, hotter, and increasingly extreme early conditions. The equations trace the history of spacetime backward, rather than describing objects moving through a pre-existing temporal background. Imagine the visible universe played in reverse. Galaxies that now drift apart draw closer across darkness. Clusters converge, starlight blue shifts, and the great web of cosmic structure becomes smoother and more compressed. As distances shrink, density rises, temperatures increase, and gravitational curvature becomes more intense within the mathematical model. The universe becomes an incandescent plasma, then an even more extreme state beyond anything laboratories can reproduce directly. Eventually, the classical description approaches a frontier where its own predictions become difficult to interpret physically. This is not simply a blank region on a map. It is a warning embedded in the equations themselves. The mathematical tools that so accurately describe planets, stars, and expanding galaxies begin to demand conditions where their assumptions may no longer hold. The familiar North Pole analogy can clarify one limited aspect of this problem without answering the cosmological question. Asking what lies north of the North Pole exposes a boundary in a particular geographical coordinate system. Northward travel ends there because every direction away from that point is southward on Earth's curved surface. The question is grammatically valid, yet its assumed direction no longer applies at the specified location. A map can display lines of longitude narrowing toward that point until they meet. A traveller may continue walking, but not by proceeding farther north. The coordinate has reached its limit, even though the physical surface continues smoothly beneath the traveller's boots. Likewise, asking what happened before time began may impose a temporal direction where none is physically defined. But the analogy must remain cautious, because Earth's pole is a known feature within already existing space and time. It has a physical surface, a surrounding planet, a measurable temperature, and a traveller who can approach it. Cosmic time may not possess an identical boundary, topology, geometry, or physical explanation. The analogy illustrates a conceptual possibility, not evidence that the universe literally has a North Pole of time. It warns against careless language while leaving the physical structure of the earliest epoch open to investigation. A coordinate failure is not always a physical failure. Longitude becomes awkward at the pole, but the ice does not vanish there. By contrast, the earliest cosmic regime may involve a more profound breakdown, where not only a coordinate but the classical notion of spacetime becomes inadequate. General relativity itself supplies some of the strongest reasons physicists take such boundaries seriously. During the 20th century, Roger Penrose and Stephen Hawking developed singularity theorems using relativity's geometric logic. Their work emerged after Einstein's theory had already transformed gravity from a force into the curvature of space-time. It also followed decades of debate about whether extreme predictions reflected reality or merely unrealistic idealizations. These theorems did not depend upon imagining a tiny object exploding into an empty surrounding void. Instead, they showed that under specified physical conditions, certain space-time paths cannot be extended indefinitely into the past. Such paths are called geodesics, the routes followed by freely moving objects and light through curved space-time. In flat space-time, a geodesic resembles a straight line. In curved space-time, it may bend, converge, or end where the theory cannot continue it. Gravity has a focusing effect in these arguments. Matter and energy curve space-time so that bundles of nearby geodesics tend to converge. Under appropriate conditions, that convergence becomes so severe that the classical description predicts an unavoidable limit. Penrose first demonstrated related behaviour in gravitational collapse, showing that singular behaviour did not require perfectly symmetrical stars. Hawking extended the reasoning to expanding cosmological models, connecting space-time geometry with the universe's past history. Past incompleteness means the classical space-time description reaches an edge where some histories cannot be continued further backward. This result is more precise than the popular claim that relativity proves an observed point of infinite density existed. A theorem can establish incompleteness under assumptions without revealing the physical nature of whatever replaces the incomplete description. The distinction is technical, but its philosophical importance is enormous. A singularity in physics is not automatically an object, a place, or an event that instruments have directly observed. It is often a sign that quantities in a mathematical model diverge beyond the regime where that model remains trustworthy. In classical general relativity, density or curvature may become unbounded when equations are extrapolated toward extreme conditions. The equations then produce an infinity, but an infinity is not a photograph of reality. It is a warning that the theoretical map has failed. A speedometer reading beyond its scale does not reveal an impossible new kind of motion. It reveals that the instrument was not designed for what it is being asked to measure. Likewise, a classical singularity may mark the point where space-time, treated as smooth and continuous, has been pushed beyond its physical domain. Physics has encountered such warnings before. Early calculations of electromagnetic radiation produced disastrous infinities until quantum theory changed the assumptions behind the calculation. Blackbody radiation, once predicted to pour infinite energy into short wavelengths, became intelligible only when energy was understood to arrive in discrete quanta. The same pattern may occur near the earliest conceivable cosmic epoch, where gravity and quantum effects should become equally important. General relativity describes dynamic space-time magnificently, but it treats geometry as fundamentally smooth and classical. Quantum mechanics describes microscopic uncertainty and fields magnificently, but it usually assumes a space-time background on which those fields operate. Near the Planck scale, those separate assumptions are expected to collide, because geometry itself may fluctuate quantum mechanically. At that frontier, distance, duration, and even sequence could become less definite than our familiar equations assume. The Planck length is unimaginably small, about 10 to the minus 35 meters. The Planck time is correspondingly brief, about 10 to the minus 44 seconds. These numbers do not identify a confirmed first instant. They mark a scale where the quantum behavior of gravity can no longer be ignored and where present theories lose their separate authority. A reliable account requires quantum gravity, a framework uniting spacetime's gravitational dynamics with quantum theory's probabilistic microscopic behavior. No experimentally confirmed theory of quantum gravity yet tells us exactly what replaced, avoided, or transcended the classical singularity. Different approaches suggest different possibilities. Some treat geometry as built from discrete quantum relationships. Others describe spacetime as emerging from deeper states rather than existing at the fundamental level. That uncertainty does not erase the hot Big Bang evidence established through expansion, radiation, element abundances, and primordial structure. The cosmic microwave background still fills the sky as a faint relic glow from a much hotter era. Hydrogen, helium, and lithium abundances preserve evidence of early nuclear processes. Distant galaxies reveal that the observable cosmos has changed dramatically over billions of years. The Big Bang strongly describes an early hot, dense, expanding phase of our observable universe. It does not directly observe a literal beginning from absolute nothing or an actual physical infinity. At the classical limit, our most successful gravitational equations are signaling that further physics is required. This boundary separates a tested cosmic history from more speculative claims about its deepest possible origin. This is where causation becomes more difficult than the question first appears. Causes, in ordinary reasoning, are earlier conditions that bring about later events through some process. That definition assumes a temporal framework in which cause and effect can be ordered. A match is struck before the flame appears. A collapsing cloud exists before it forms a star. A signal is emitted before it reaches a receiver. If time began with the earliest physical epoch, what could earlier possibly mean in that context? The phrase, "what caused the universe before it existed," may be grammatically familiar but physically undefined. It may combine useful words into a question whose underlying temporal assumptions fail at the boundary. This possibility is not an evasion, nor does it claim that the universe needs no explanation. It distinguishes between asking for an explanation and demanding an earlier event when earlier may not exist. An explanation might involve laws, boundary conditions, quantum states, symmetries, or principles not operating as temporal causes. It might describe a logical relationship rather than a sequence of events. Or it might require a deeper framework in which time emerges from something more fundamental and unfamiliar. We do not yet know which possibility, if any, nature chooses, but we should not force cosmic reality into categories built for events occurring within already established time. the deepest mystery changes shape when time is no longer treated as an unquestioned external backdrop. Rather than asking only what happened before, we must ask whether before is a meaningful physical relation here. Rather than asking only what caused time, we must ask how time becomes part of a describable universe. These are difficult questions because language evolved to navigate ordinary sequences, not the foundations of sequence itself. Our verbs carry temporal assumptions almost invisibly. To begin, emerge, produce, precede, and become all seem to point along a timeline. What happens when the timeline itself is part of the problem? The problem becomes sharper when modern cosmology examines models that appear eternal at first glance. Inflation proposes that a brief era of accelerated expansion helped establish the large-scale smoothness of the observable universe. During such expansion, tiny regions could be stretched to enormous scales, making distant parts of the sky appear remarkably similar. Small quantum fluctuations would also be enlarged, eventually helping seed galaxies and cosmic structure. Some versions suggest inflation continues eternally in distant regions, generating many expanding domains through an ongoing larger process. Such proposals can seem to avoid a beginning by placing our visible universe inside a continuing cosmic landscape. In visual terms, one may imagine bubbles forming within a vast frothing expanse, each developing its own local history. Yet even this evocative picture risks assuming a larger arena whose status remains unexplained. A major result called the Borde-Guth-Vilenkin theorem complicates that conclusion. Arvind Borde, Alan Guth, and Alexander Vilenkin showed that many eternally expanding spacetimes remain past incomplete under broad conditions. Their theorem concerns a positive average expansion rate along certain past-directed paths through spacetime. If expansion remains positive enough on average, those paths cannot be extended arbitrarily far into the past. This includes many inflationary scenarios, even models that continue generating new expanding regions far into the future. The theorem suggests that expansion alone does not supply a complete infinite past for such cosmologies. Its power lies partly in what it does not require. It does not depend upon detailed assumptions about the exact matter, content, or a particular theory of gravity at every stage, but it does not prove that everything emerged from literal nothing at a single first instant. It does not establish which quantum gravitational physics might operate beyond the classical description's past boundary. It does not rule out every cyclic, bouncing, emergent, or otherwise non-classical alternative proposed by theoretical cosmologists. It says that a particular class of descriptions needs something beyond its own eternally expanding behaviour. The distinction matters because scientific results are often enlarged into metaphysical conclusions they cannot rigorously support. Past incompleteness is not the same as creation from nothing. A boundary in one mathematical description is not automatically a final boundary for all possible physics. The theorem intensifies the origin problem, but it does not settle it. It tells us that many expanding models cannot simply extend familiar expansion forever backward without encountering a limit. What lies at that limit may depend on quantum gravity, unknown initial conditions, or a reformulation of spacetime itself. The boundary could be a transition rather than an absolute beginning. It could reveal a previous phase, or it could expose a category of physical description we have not yet learned to formulate. The demand for a beginning also involves another feature of cosmic history that remains profoundly unexplained. Time appears to have an arrow, a direction distinguished by increasing entropy and the irreversible growth of disorder. We remember the past rather than the future because records, memories, and physical traces form within that asymmetric history. A photograph records a moment after light reaches film or a sensor. A footprint remains after a foot presses into wet ground. Broken objects do not spontaneously reassemble. Heat flows from warmer bodies toward cooler ones, and stars consume usable energy. The fundamental microscopic laws often permit time-reversed processes, yet macroscopic experience overwhelmingly displays a preferred direction. A movie of shattered glass reforming looks immediately unnatural, although many equations governing individual particles are not so obviously biased. The arrow emerges from the overall condition of vast numbers of particles and fields. Cosmology connects that direction to the extraordinarily ordered condition of the early universe. Entropy measures, roughly, how many microscopic arrangements can realize the same broad physical state. A state with many possible arrangements has high entropy. A state confined to comparatively few arrangements has low entropy. This is why gases diffuse through rooms and why mixed substances rarely separate spontaneously. The early universe was hot and nearly uniform, a condition that might sound disordered in ordinary thermal language. But gravity changes the story because a smooth distribution of matter has remarkably low gravitational entropy. In a universe governed by gravity, clumping is usually favoured. Matter can collapse into stars, galaxies, dense remnants, and black holes, opening vastly more ways to organise the gravitational field. A smooth early cosmos was therefore not merely a featureless fog, it was an exceptional starting condition with enormous capacity for later entropy increase. Tiny variations in density, visible today as faint temperature differences in the cosmic microwave background, became the seeds of later structure. Gravity amplified them over immense spans of time, drawing matter into filaments, clusters, luminous galaxies, and eventually worlds where chemistry could become intricate. That low entropy beginning made the arrow of time possible. It allowed gradients, structure, chemistry, life, memory, and the unfolding complexity visible throughout cosmic history. Every living system depends upon energy flowing from concentrated sources toward more dispersed forms. Plants use sunlight, planets radiate heat, and biological order persists only by increasing entropy elsewhere. The direction we call future is written into this cosmic imbalance, yet the laws governing later evolution do not clearly explain why the initial condition possessed such extraordinary order. Inflation may account for some observed smoothness, but it does not automatically resolve the deeper entropy question. Any inflationary beginning may itself require special conditions, and proposed explanations remain debated. The puzzle is especially sharp because gravity makes smoothness so unusual, not so natural. The arrow of time is therefore not merely a consequence of clocks moving forward. It is tied to a cosmological fact about the universe's initial state that remains unexplained. The earliest observable chapter appears to have been arranged in a way that permitted irreversible history to unfold. Why should the universe have begun in a condition so unlike the high entropy states it could have occupied? This fact deepens the paradox at the centre of our investigation. Even if time began with the Big Bang, why did the beginning contain conditions from which time and complexity could unfold? Why was there a state with physical regularities, possible change, and extraordinarily low gravitational entropy? Why did reality possess the capacity for galaxies, stars, planets, observers, and questions about its own emergence? Saying that no earlier time existed may dissolve one form of causal demand without dissolving these deeper questions. The absence of a temporal before would not turn the initial condition into an explanation of itself. It would instead reveal that explanation may require concepts beyond ordinary causes and earlier events. A timeless boundary, if such a phrase is ultimately meaningful, could still demand a physical account. Perhaps the earliest condition was necessary under deeper laws. Perhaps it was contingent among many possibilities. Perhaps selection effects, quantum principles, or structures beyond present theories will offer part of an answer. Perhaps the question reaches a boundary where physical explanation and philosophical explanation ask different things. None of these possibilities is established, and none should be disguised as a conclusion. The responsible position is more demanding than either certainty or surrender. We possess powerful evidence that the observable cosmos evolved from an early hot, dense state. We possess strong reasons to think classical physics becomes incomplete near the earliest conceivable regime. We do not possess a confirmed account of why that regime had its particular laws, state, entropy, or capacity. This gap is not empty ignorance. It is a map of specific problems connecting gravity, quantum mechanics, thermodynamics, and the meaning of time. Each problem has a defined edge. General relativity succeeds spectacularly, yet becomes singular when extrapolated too far. Quantum theory succeeds spectacularly, yet does not fully explain the spacetime stage it usually assumes. Thermodynamics explains increasing entropy, yet leaves the astonishingly low initial entropy unresolved. Quantum gravity stands at the centre, because general relativity makes spacetime dynamic, while quantum theory makes physical systems fundamentally uncertain. A unified theory may reveal that spacetime is granular, emergent, relational, or replaced by deeper quantum structures. It may show that the classical singularity becomes a finite quantum phase rather than a literal endpoint. It may show that time changes character near the boundary, becoming approximate rather than fundamental. Or it may reveal possibilities no current language describes adequately. The challenge is not merely to invent an elegant mathematical picture. A successful theory must recover relativity and quantum mechanics, where both have been tested, while offering new consequences that observation can eventually examine. Until such a theory is tested, confident stories about the first moment remain premature. The Planck era names an extrapolated frontier where densities, energies, and curvatures approach scales beyond current direct experimental reach. At those scales, the smooth space-time picture used by classical relativity may no longer apply. A before may become ambiguous because time itself could emerge only in a later semi-classical phase. A location may become ambiguous because space could emerge alongside the physical relations that define locations. A vacuum may become ambiguous because quantum fields normally assume some version of space-time and temporal evolution. The concepts explored in earlier chapters may therefore converge and fail together near the origin frontier. Nothing, vacuum, space, time, law, cause, and beginning cannot simply be separated there with everyday confidence. They may be distinct concepts within familiar physics, yet only approximate descriptions near its deepest boundary. This does not mean that science has reached nonsense. It means precision requires admitting where present concepts cease to be securely applicable. The question "did nothing start the Big Bang?" remains open, because nothing itself is not a simple scientific starting point. Absolute nothing has no space, time, fields, laws, potential, or mechanism from which an event could proceed. A quantum vacuum is something structured. It contains fields, fluctuations, and lawful behavior. A past incomplete spacetime is something described by a limited theory. A singularity is something indicated by equations failing under extreme extrapolation. None is identical to absolute non-being, however dramatic popular language may make them sound. The strongest conclusion remains careful. The Big Bang is strongly supported as the beginning of our observable, hot, expanding cosmic history. Science has not established that absolute nothing created everything. It has instead revealed that time, space, causation, vacuum, and nothingness may be emergent or incomplete concepts. The mystery survives not because evidence is absent, but because evidence leads directly toward the limits of our present frameworks. Those limits now open toward competing proposals, each attempting to describe what classical language cannot securely reach. Some models imagine a quantum event producing an expanding universe from a prior physical state or formal possibility. Some describe a bounce, where contraction gives way to expansion without a classical singularity. Some place our observable region within a larger cosmic process extending beyond the history we can directly observe. These are not final answers to why anything exists. They are bold attempts to replace an incomplete boundary with a calculable physical account. Their success will depend on mathematical consistency, observational consequences, and clarity about what they assume from the beginning. A proposal does not explain absolute nothing merely because it removes a singularity from an equation. The next chapter enters those possibilities without mistaking speculation for proof. It asks whether a universe can emerge through quantum tunneling, rebound from an earlier phase, or arise within a wider cosmic process. Each possibility confronts the same stubborn question. Does it explain existence, or does it move the mystery into a deeper framework? When time has no earlier, the search for causes does not end. It becomes stranger, more exacting, and more honest. At the edge of the cosmic story, the universe does not offer a simple answer. It offers a boundary illuminated by evidence, where our oldest question must learn a new language. At the frontier where classical spacetime fails, cosmology asks whether quantum principles can describe a universe without assuming an earlier conventional moment of time itself. Earlier chapters separated absolute nothing from vacuum, space, laws, and time, then showed why the Big Bang does not directly establish creation from non-being. That distinction becomes even more important here, where familiar words acquire technical meanings that can quietly differ from their ordinary philosophical use. Quantum cosmology seeks a description in which quantum mechanics applies not merely to particles or laboratories, but to the universe considered as one system. It is an audacious extension of a theory developed through experiments with atoms, light, and microscopic particles into the domain containing every experimenter and instrument. That ambition immediately disrupts ordinary quantum theory, where experiments distinguish an observer, a measured system, an apparatus, and an external clock governing change outside. A laboratory can be treated as a stable stage, while a detector records outcomes and a clock marks the passing seconds. For the universe, no observer can stand outside all reality, no apparatus can be entirely external, and no background spacetime is automatically available either. The stage, the actors, the measuring devices, and the clocks may all be woven into one quantum description. The observer, system, and geometry may belong to one quantum description, making familiar divisions between what measures and what is measured fundamentally uncertain there. Even the phrase "the state of the universe" becomes difficult, because states are ordinarily defined relative to time, measurements, and a surrounding framework. This is not simply physics scaled upward, because the cosmic arena normally used to define states and observations becomes part of the problem itself. Imagine trying to map a landscape while the paper, compass, observer, and horizon all fluctuate according to the same underlying rules. Quantum gravity therefore asks how matter, geometry, probability, and perhaps time can be described together, when none may serve as an unquestioned backdrop alone. General relativity treats spacetime as dynamic, curved by energy and matter, while quantum mechanics describes uncertainty and superposition with extraordinary precision. Bringing those achievements together has resisted generations of effort. Near ordinary densities, either framework works remarkably well, but near the earliest imaginable conditions, their assumptions collide with unusual force. No confirmed theory yet answers that question, but several influential proposals show how radically the meaning of a beginning might change there under quantum. They are not settled descriptions of reality, yet they reveal precisely where everyday intuition begins to lose its grip. One famous clue comes from an equation whose very form challenges the ordinary picture of a universe progressing through an independently ticking time parameter. Its name evokes two major figures in 20th century theoretical physics, John Wheeler and Bryce DeWitt. The Wheeler-DeWitt equation is a proposed quantum gravitational equation intended to describe possible states of the universe, including its geometry and matter contents. Developed during attempts to quantize Einstein's general relativity, it treats the gravitational field itself as something that may possess quantum possibilities. In simplified language, it resembles a constraint rather than a usual evolution equation, linking allowed cosmic configurations without obviously placing them inside external time. Instead of saying, "this state becomes that state at a later instant," it can resemble a rule that allowable total states must satisfy. Physicists often represent these possibilities using a wave function of the universe. Rather than assigning an ordinary location to one particle, this formal object can assign amplitudes across an immense landscape of possible spatial shapes and matter arrangements. That landscape is sometimes called superspace, though it is not a hidden region through which spacecraft could travel. It is an abstract mathematical space whose points correspond to different possible geometries of space itself. Its exact interpretation depends on the approach to quantum gravity, and physicists still debate what its solutions mean for an actual universe physically today. The equation is formidable even in simplified models, and full realistic calculations remain far beyond straightforward solution. Yet the missing external time is striking, because ordinary quantum equations usually predict how states change as a specified clock parameter advances forward continuously. In the familiar Schrödinger equation, time stands outside the system, quietly directing the sequence of change. Here, time may be hidden within relationships among variables, emerge only approximately, or require a different interpretation of what counts as change at all. A changing correlation between one physical quantity and another might function as a clock, even when no universal clock appears fundamentally. For example, a particular matter field could increase in one direction, while the geometry changes with respect to it. In that limited sense, one variable can tell a story about another, without requiring an external cosmic stopwatch. This difficulty is called the problem of time, and it reaches beyond terminology into the foundations of cosmic explanation and causation itself as well. Cause normally comes before effect, but before becomes uncertain if time is not present at the deepest level. If fundamental equations lack ordinary time, then a first moment may not be a basic ingredient, even where later clocks clearly operate normally today. The first tick of every clock could belong to an emergent era, not necessarily to the deepest physical description. Our experience sequence could arise after the universe enters a regime where geometry becomes sufficiently classical, stable, and capable of supporting physical clocks reliably. In such a regime, quantum alternatives may become effectively separated, allowing definite histories to emerge on large scales. This process is often associated with decoherence, where interactions with many surrounding degrees of freedom suppress visible quantum interference. The underlying quantum description may remain, yet familiar objects begin behaving as though they possess stable classical properties. That possibility does not prove time emerged, but it warns that questions about earlier causes may use concepts unavailable at the deepest quantum level. A question can be grammatically clear and still rely upon categories that nature does not fundamentally provide. The mystery now shifts from what happened before the Big Bang toward what kind of quantum description could make later time intelligible at all. Against that unsettling background, proposals about a cosmic beginning take on a meaning far stranger than a simple first explosion. James Hartle and Stephen Hawking proposed one celebrated answer, called the no-boundary proposal, which replaces a sharp initial edge with smooth finitude instead. Their work emerged from efforts to apply quantum ideas to the entire cosmos without inserting a singular beginning by hand. In their model, the earliest universe may be finite yet lack the temporal boundary that ordinary language imagines as an abrupt beginning point entirely. Finite does not automatically mean bounded, just as a complete surface can have a limited area without an edge. The analogy to a rounded surface is useful only in limited ways, because one can travel without encountering an edge or boundary anywhere there. On Earth, a traveller moving north reaches the pole, not a cliff where the surface simply terminates. Near the proposed origin, a Euclidean geometry can close smoothly, much as a polar region avoids a jagged edge on an idealized sphere surface. The visual is not of a universe beginning at a hard wall, but of a geometry rounding gently into a different mathematical form. This image does not mean the universe is literally a sphere, nor does it identify a physical place beyond which travel becomes impossible forever. It concerns the geometry of the earliest mathematical description, not a location inside a larger ordinary space. The proposal uses imaginary time, a mathematical transformation in which time coordinates are represented differently, helping certain geometries become smooth and calculable near origins. This technique has deep roots in quantum theory, where it can turn oscillating equations into forms resembling statistical behavior. Imaginary here means multiplication by a mathematical factor involving the square root of -1, not a hidden dimension available to travelers or spacecraft. The word can sound mystical, but its role is precise. It changes how intervals are handled within an equation. In ordinary spacetime, time and space contribute differently to the mathematical interval between events. Under the relevant transformation, that distinction is altered, producing a Euclidean-like geometry in which certain singular features may be treated more smoothly. It is a technique that can connect quantum calculations with geometries resembling ordinary space, while changing the signature used to measure intervals mathematically only. Afterward, physicists must still confront the difficult question of how such a calculation relates to the time-filled universe we observe. No-boundary models therefore should not be translated into claims that time physically turns into a navigable spatial corridor at the beginning itself, literally. The mathematics offers a way to formulate a quantum state, not a tourist map of the primordial cosmos. The formal move may be powerful because it avoids a singular sharp endpoint within the model, replacing it with a regular quantum geometry instead. Classical general relativity predicts singular behavior when extrapolated backward, but singularities often signal that a theory has reached the edge of its authority. Its wave function assigns amplitudes to possible cosmic histories, expressing which large-scale geometries and matter arrangements are weighted by the proposal mathematically there. One can picture a vast ensemble of candidate universes, each carrying a different quantum weight rather than a simple label of possible or impossible. In quantum theory, an amplitude is not a simple story about one observed event, but part of calculating probabilities for possible outcomes or histories. Amplitudes can reinforce or cancel one another, a feature responsible for interference patterns in experiments and conceptual difficulty in cosmology. The no-boundary proposal has inspired substantial work because it offers a precise alternative to a classical singularity and connects naturally with inflation models. In some versions, smooth initial conditions can be linked to the later onset of accelerated cosmic expansion. Some calculations suggest it can favour particular broad classes of early universes, though conclusions depend strongly upon assumptions, approximations, and chosen measures within calculations. Small changes in how the mathematical sum is defined can alter which histories appear most strongly weighted. Critics debate technical questions involving path integrals, contour choices, probabilities, and whether the proposal uniquely defines the quantum state required for cosmic description itself. A path integral, in broad terms, sums contributions from many possible histories rather than selecting one classical route in advance. For a particle, the idea is already subtle. For spacetime itself, the sum may include geometries so varied that deciding precisely what should be counted becomes a profound technical challenge. Even supporters do not claim that smooth geometry demonstrates absolute non-being somehow possessed a tendency, a law, or a plan to create reality itself. The proposal begins with a formal language capable of describing possible geometries and assigning them quantum amplitudes. It may eliminate a prior classical spacetime from the description, yet it does not eliminate mathematics, possibility, or the laws organizing possible descriptions themselves. The sharp physical question may be softened, while the deeper metaphysical question remains illuminated by contrast. The central question remains sharpened rather than answered. What makes such a quantum framework real, applicable, or available before cosmic history begins at all? Alexander Vilenkin offered a contrasting picture, often called tunneling from nothing, in which an expanding universe quantum mechanically appears from no classical spacetime background. The phrase is arresting, and it has become influential far beyond specialist discussions of quantum cosmology. Tunneling is a familiar quantum phenomenon, where systems cross barriers forbidden by classical motion, because quantum states assign non-zero amplitudes beyond those barriers sometimes. It does not mean an object drills through material. It means the quantum description extends into regions classical physics excludes. Radioactive decay supplies an everyday example. A particle confined within a nucleus can tunnel through a barrier and emerge without classical escape being possible. The particle is not given enough classical energy to climb over the barrier, yet decay still occurs with a calculable probability. Modern technologies, including scanning tunneling microscopes and some electronic devices, depend on related quantum behavior. Tunneling is therefore not speculative in itself. Only its application to an entire possible universe is extraordinarily unfamiliar. In cosmology, the analogy becomes far stranger, because the tunneling object is not a particle within space, but an entire possible spacetime history itself. The barrier is represented within an abstract configuration space, involving quantities that characterize cosmic size, matter, and geometry. Vilenkin's language of nothing usually refers to an absence of classical space and time, not the philosophical absence of every property or condition whatsoever. There may be no pre-existing landscape, no conventional clock, and no earlier material universe in the ordinary sense. The distinction is decisive because the tunneling calculation still presupposes a wave function, a configuration space, and quantum rules governing allowed alternatives there formally. It needs a structured arena of possibility, even if that arena is mathematical rather than spatial. It also uses a gravitational theory to define quantities resembling scale, energy, and geometry, even if no classical spacetime exists before tunneling within models. Without such ingredients, there is no barrier to tunnel through, no amplitude to calculate, and no transition to describe. Calling that starting condition nothing can be rhetorically dramatic, but it risks concealing the rich mathematical structure required for tunneling to mean anything coherent. The issue is not wordplay, because different definitions lead to fundamentally different explanatory claims. A quantum transition may avoid a prior universe with stars, atoms, or familiar clocks, while retaining a theory of possible universes and transitions between them. That is already a radical departure from ordinary causal stories, where one event follows another within a shared temporal setting. That is a profound reduction of assumptions compared with ordinary creation stories, but it is not creation from absolute non-being in the strict sense. A law-governed quantum possibility is not empty of structure merely because it lacks classical space. The question becomes whether laws can exist without space-time, whether wave functions require interpretation, and whether possibility itself demands an explanatory ground beyond physics. Physics can clarify consequences of formal assumptions, but it may not determine why formal assumptions obtain. Physics can formulate and compare such models, but it cannot simply label their mathematical prerequisites nothing without changing the meaning of the original question. Precision here is not an obstacle to wonder, it is what prevents wonder from becoming confusion. The word nothing therefore remains under interrogation. Does it mean no particles, no classical geometry, no prior time, or no reality whatsoever in principle? Each answer names a different claim, and only the last approaches the absolute absence that ordinary philosophical language usually intends by nothing itself there. The difference between an empty stage and the absence of any stage, rules, or possibilities is immense. While origin proposals confront the boundary directly, inflation addresses a different problem. It seeks to explain why the young observable universe had particular conditions. Inflation proposes an extremely brief epoch of accelerated expansion, during which distances grew enormously faster than they would under ordinary hot Big Bang expansion. The proposed period may have lasted far less than a second, yet its consequences would extend across billions of light years. It does not describe galaxies flying through empty surroundings. It describes space-time expanding so rapidly that initially nearby regions became vastly separated from each. Like dots drawn on an inflating balloon, the galaxies later move apart because the underlying geometry changes. Before inflation, regions now far apart may have been close enough to exchange energy and approach similar temperatures, explaining broad cosmic uniformity today observed. When inflation stretched that small region outward, it preserved the imprint of its earlier shared conditions. The microwave background is nearly uniform across directions that standard expansion alone struggles to connect causally, a puzzle called the horizon problem historically there. This ancient radiation, released when the universe became transparent roughly 380,000 years after the hot Big Bang, forms a faint glow across the entire sky. Its temperature varies by only tiny fractions, even between regions whose light could not have travelled between them under a simple, non-inflationary history. Why should such distant patches appear so closely matched, as though they once exchanged information? Inflation stretches a tiny connected patch until it encompasses the observable sky, making its common temperature less surprising within the proposed early history today. A region once smaller than an atom could, in principle, become the ancestor of scales now beyond our visual reach. It also addresses flatness, because rapid expansion can drive spatial curvature toward near zero, much as a small surface patch can appear flatter locally. Any initial curvature is diluted as space expands, leaving the observable region looking increasingly level on the largest measured scales. Measurements indicate that large-scale cosmic geometry is remarkably close to flat, although exact global shape and total extent remain observationally unsettled even now. The universe may be vastly larger than the observable region, and its total geometry could remain inaccessible to direct measurement. Inflation does not prove space is perfectly flat. It explains why observable curvature could be diluted below present measurement sensitivity after tremendous expansion occurred. The distinction matters because a successful mechanism for near flatness is not a direct measurement of infinite extent. The same mechanism offers a third success. Quantum fluctuations in fields could be stretched from microscopic scales to astronomical scales during accelerated expansion itself. What began as unavoidable quantum uncertainty could become a visible pattern written across the sky. Initially, tiny variations would become slight differences in density and gravitational potential, leaving patterns later visible in the microwave background and galaxy distribution today. The resulting temperature mottling appears as a delicate celestial map, with warmer and cooler regions differing by mere millionths of a degree. Gravity then amplified denser regions, drawing matter into filaments, clusters, and galaxies, while less dense regions became the vast cosmic voids between structures eventually. In computer simulations, the process produces a luminous cosmic web, where narrow strands connect dense knots across immense black gulfs. This is a striking connection. Randomness at quantum scales may have supplied the seeds for every galaxy, star, planet, and observer in view today. The atoms in a human body may owe their eventual arrangement, in part, to fluctuations born in a primordial quantum state. The observed pattern is not arbitrary, because inflationary models predict statistical properties that can be compared with precise maps of cosmic background radiation measurements. Researchers examine the distribution of fluctuations across angular scales, searching for correlations that a simple random pattern would not naturally produce. Satellite observations have found fluctuations broadly consistent with simple, inflationary expectations, including near-scale invariant patterns and correlations across the early cosmic sky maps. Missions such as COBE, WMAP, and Planck transformed faint microwave variations into some of cosmology's most informative evidence. Broad consistency matters, but it does not identify one unique inflationary model, one unique field, or one confirmed account of cosmic origins today directly. Many different models can generate similar broad predictions, especially when their parameters are adjusted within plausible ranges. Most versions invoke an inflaton, a hypothetical field whose energy temporarily drove accelerated expansion. Though no experiment has identified this field conclusively so far, its name is functional rather than explanatory. It identifies the role required by the model, not the field's confirmed microscopic identity. The inflaton may represent a new fundamental field, an effective description of deeper physics, or a placeholder for mechanisms not yet understood by science. In some proposals, it is associated with particle physics at energies far beyond any current accelerator. Its potential energy must possess a suitable shape, allowing expansion to persist long enough, then change so ordinary particles and radiation can emerge afterward. Physicists often visualize this with a ball rolling slowly across a gently sloping landscape, though the picture is only a simplified analogy. This ending is called reheating, when energy associated with inflation is transferred into hot matter and radiation, launching the familiar hot Big Bang evolution. The cosmos must become filled with particles again, otherwise inflation would leave an expanding but almost empty and frigid universe. Reheating is essential, because inflation alone would leave a cold, dilute universe, rather than the energetic particle-filled plasma supported by early evidence today. It creates the bridge between a hypothetical accelerated phase and the hot radiation-dominated era described by standard cosmology. Models must explain why inflation began, what set its initial conditions, why it lasted its required duration, and how reheating proceeded consistently afterward physically. These are not decorative additions added after the main idea, but central requirements for a complete physical account. Those questions are not peripheral details. They determine whether inflation is predictive physics or a flexible framework adjusted after observations appear in our sky. Different potentials and starting assumptions can generate similar observable universes, making it difficult to determine which version, if any, nature actually selected historically there. The more versions reproduce existing data, the more important genuinely distinctive future tests become. One anticipated signature is primordial gravitational waves, faint ripples in space-time that some inflationary scenarios predict should imprint characteristic polarization patterns on ancient radiation. Such waves would carry information from an extraordinarily early epoch, when energies may have been unimaginably high. Scientists search for these patterns, often called B modes, because a convincing detection could reveal the energy scale and dynamics of inflation itself directly. On a sky map, the effect would appear as a subtle swirling orientation in the polarization of microwave light. Foreground dust within our galaxy can imitate or obscure the sought signal, so extraordinary care is required before announcing evidence for primordial waves confidently. A celebrated early claim in 2014 showed exactly why caution matters, when galactic dust proved capable of producing a misleading pattern. Other observations constrain inflation through the spectrum of density fluctuations, non-Gaussian features, spatial curvature, and relic particles predicted by particular models as well. Each measurement narrows the landscape of possibilities, though it has not yet isolated a single uncontested explanation. So far, the evidence supports an early mechanism resembling inflation more strongly than it confirms any complete underlying inflationary theory beyond dispute for researchers. That is a meaningful scientific success, but it is not the final word on the cosmic beginning. Inflation's achievements are therefore real but conditional. It can explain features of the hot Big Bang without necessarily explaining why its own ingredients existed. It may describe the preparation of our observable cosmic history rather than the ultimate origin of fields, laws, space-time, or the inflationary state itself. A mechanism can explain how a particular arrangement evolves while leaving open why that mechanism was available. This distinction returns us to the opening question. A successful account of early evolution is not automatically an account of why anything exists whatsoever. Even if quantum fluctuations seeded galaxies during inflation, the fluctuating fields, their quantum state, and the governing rules remain part of the starting story. Even if those ingredients arise from deeper physics, the request for explanation may simply move one level further downward. Even if a tunneling proposal avoids classical time, its amplitude, configuration space, and quantum law remain ingredients rather than absolute absence or silence itself. The word "from" can conceal a great deal when no ordinary temporal sequence is being claimed. Even if no boundary geometry removes a sharp edge, the proposal still asks us to accept a framework capable of describing smooth possibilities mathematically. It may transform the shape of the question without dissolving the question completely. None of these models is worthless for retaining assumptions. Their value lies precisely in exposing assumptions that can be clarified, tested, and challenged openly. The mistake would be demanding that a physical model answer every philosophical question, or declaring philosophical closure because a physical model is elegant mathematically. Different disciplines may approach different layers of the same mystery without one invalidating the other. Science advances by making starting assumptions explicit, deriving consequences, and confronting them with evidence. It does not gain certainty by renaming assumptions nothing there. The vocabulary matters because nothing without laws, states, possibilities, space, and time cannot tunnel, fluctuate, expand, or select an outcome in any usual sense. Every one of those verbs quietly invokes a framework in which something can happen. If it has a quantum disposition to produce universes, then it already possesses a disposition, a rule, and a structure unlike absolute nothing itself. If it can be described, compared, or assigned a probability, it is not sheer conceptual blankness. If it exists before an event, then before has already supplied time. If it contains potential, then potential has supplied physical content as well. Absolute non-being cannot wait, obey equations, possess probabilities, or transform. Those verbs describe conditions within some framework, not the absence of frameworks altogether themselves. This does not make the origin question meaningless. It makes it more exacting because every proposed beginning must declare what it assumes and explains. Once assumptions become visible, another possibility enters view. Perhaps the apparent beginning was not an absolute origin, but a transition within wider reality itself. Some models reject a single beginning altogether, proposing a contraction before expansion, recurring cycles, an emergent phase, or a larger multi-regional cosmos beyond ours. These ideas differ dramatically, but each asks whether the hot Big Bang marks a threshold rather than the first page. A bounce model imagines an earlier contracting universe reaching extreme density, then avoiding a classical singularity through quantum gravitational effects and re-expanding again afterward. The visual is of a cosmic collapse that does not end in an infinite point, but reverses through an unfamiliar quantum regime. Such scenarios might replace the first instant with a rebound, but they require a mechanism that remains mathematically consistent and observationally distinguishable from inflation. A bounce is not established merely by replacing an unwanted singularity with an appealing image of renewal. Cyclic models propose repeated expansions and contractions, though entropy growth, stability, and the transfer of information across cycles pose serious unresolved challenges for them. If disorder increases from cycle to cycle, how can the universe repeatedly return to conditions suitable for a fresh beginning? Emergent universe proposals seek a long-lived prior state that evolves into expansion, yet they must explain why that state persisted and changed eventually. A nearly eternal calm may postpone the beginning problem, but it does not automatically resolve the reason for its eventual departure. Eternal inflation pictures continuing expansion in a broader setting, with local bubble universes forming as different regions undergo transitions and develop separate histories thereafter. Our observable universe could be one bubble among many, though the larger setting may remain permanently beyond direct observation. But past incompleteness results warn that many eternally expanding descriptions still cannot be extended indefinitely backward, leaving a boundary or new regime requiring explanation. The warning is mathematical, not a cinematic proof that the cosmos suddenly emerged from literal nothing. The Borde-Guth-Vilenkin theorem does not prove creation from nothing. It shows that sustained average expansion may not provide a complete cosmic past. Its conclusion depends on defined conditions and does not determine what lies beyond the mathematical limit, whether quantum transition, bounce, or something unknown entirely. A theorem can identify where a model's extrapolation fails without supplying the physical replacement required beyond that boundary. No current alternative has earned confirmation as the universe's ultimate prehistory. Each illustrates how the Big Bang might be one chapter, not every chapter. The observable hot expansion could have followed a rebound, emerged from a quantum state, or begun locally within conditions forever hidden beyond observation today. The evidence accessible to us may always be filtered through the horizon of the observable universe. These possibilities raise the stakes rather than lowering them, because they ask whether a deeper theory can turn speculative stories into discriminating scientific predictions. Can a model leave a trace in gravitational waves, particle abundances, curvature, or the detailed pattern of primordial fluctuations? A theory of origins must recover the tested hot Big Bang history, explain or predict new evidence, and state clearly where its authority ends. Mystery is not a substitute for prediction, yet the absence of final answers does not make disciplined speculation meaningless. The deepest lesson is not that science has discovered nothing created everything. It is that familiar categories may emerge only within cosmic history itself. Space, time, causation, vacuum, and perhaps even law may be less like eternal containers than features arising within a deeper quantum reality still unknown. If so, the universe's beginning may resist the language inherited from ordinary experience, where every event occurs somewhere and sometime. We stand inside a late structured cosmos, using clocks forged in stars and equations written by minds produced through cosmic evolution. From that vantage point, it may be impossible to picture the deepest origin without importing assumptions that belong only to the universe after it became familiar. The next chapter examines models without a single beginning, asking whether our origin was a transition, rebound, or local chapter within a larger universe. The hot Big Bang remains the best tested account of our observable universe's early, dense, expanding thermal history and its later evolution. It describes a universe that was once hotter, smaller, and filled with an almost uniform sea of radiation and particles. As space expanded, that primordial fire cooled, allowing nuclei, atoms, stars, galaxies, and eventually observers to emerge. The evidence is powerful: cosmic expansion, the microwave background, and the measured abundances of light elements all point toward this hot early phase. Yet the hot Big Bang model does not demonstrate that this history began from absolute nothing. Nor does it establish that no physical phase existed before the era our equations can reliably describe. When classical general relativity is pushed backward toward extreme density, it predicts singular behavior. Density, temperature, and space-time curvature appear to race toward infinity. Such infinities are often less like physical destinations than warning lights on a theoretical instrument panel. At that classical limit, general relativity signals that its smooth description of spacetime has reached failure. The theory has been extraordinarily successful across planets, black holes, gravitational waves, and the expanding cosmos. However, it treats spacetime as continuous, while quantum physics governs matter and energy at the smallest known scales. Near the apparent beginning, both descriptions are required at once, and they do not yet fit together completely. Quantum gravity may replace that failure with a deeper account, although no candidate currently possesses decisive experimental confirmation. One possibility is that the Big Bang was not an absolute beginning, but a transition from an earlier cosmic phase. These proposals replace a singular endpoint with a bounce, a renewal, a collision, or a wider process beyond our observable horizon. In each case, the familiar image of creation exploding into empty space gives way to something stranger, a transformation of space-time itself. The appeal is immediate because a transition seems more physically intelligible than reality abruptly appearing without earlier conditions. A transition, however, still requires equations, states, mechanisms, and evidence capable of distinguishing it from competing cosmic histories. It is not enough to move the mystery behind a curtain labeled before. The deeper phase must be physically coherent, mathematically controlled, and connected to observations made in the universe around us. Such models do not automatically restore an ordinary before, since time itself may behave differently near quantum gravitational extremes. The word before assumes a sequence of moments, each following another along a stable temporal direction. But near the regime where classical spacetime dissolves, that familiar ordering may no longer be fundamental. Time could remain meaningful in a transformed form, emerge only approximately, or become inseparable from the changing geometry of the universe. Yet these possibilities challenge the assumption that the earliest hot expansion was necessarily the first physical chapter of all. The central question changes shape once again. Did nothing start the Big Bang, or did the Big Bang transform something deeper? The distinction is not merely philosophical. It determines whether cosmology seeks an origin event, a boundary of knowledge, or a bridge connecting our universe to an earlier physical history. A bounce imagines a contracting cosmos reaching extraordinary density, then reversing into the expanding hot universe we observe today. On screen, a vast field of galaxies could slowly draw inward, their separation shrinking as the darkness between them narrows. The sky would not collapse toward a central point, because cosmology has no ordinary center. Instead, every large-scale distance would contract as the geometry of space itself changed. Its basic claim is modest. Classical collapse may not continue indefinitely because quantum gravitational physics becomes important before infinite density occurs. During contraction, matter, radiation, curvature, and quantum geometry would evolve toward conditions inaccessible to direct experiments. The crucial event is not an explosion into space, but a reversal in the behavior of space-time itself. Space contracts, reaches an extreme but finite regime, and then begins expanding again. This reversal could connect a pre-bounce history to our post-bounce expansion, replacing a classical singularity with finite quantum evolution. That possibility would give cosmic time a longer story, though perhaps not one describable by familiar clocks throughout. A clock depends on regular processes, orbiting bodies, vibrating atoms, decaying particles, or some repeated physical rhythm. Near a bounce, the universe may become so compressed that those ordinary markers lose their clear meaning, but a bounce is not established because it removes an uncomfortable infinity from equations or offers an appealing narrative of renewal. Researchers must show exactly what matter, geometry, and quantum effects produce contraction, stability, reversal, and later hot expansion. They must also explain why the universe after the bounce looks remarkably smooth across enormous distances. Thus, the singularity problem becomes a demanding program of physical construction. Rather than a license for confident stories about cosmic rebirth, contracting universes face hazards that expanding universes can sometimes avoid through dilution of irregularities, curvature, and unwanted particle populations. In an expanding universe, many disturbances are stretched thin as space grows. During contraction, the opposite tendency can dominate. Small ripples can become larger, regions can evolve unevenly, and directional distortions can gain strength as the total volume falls. Classical contraction tends to amplify inhomogeneities, anisotropies, and gravitational disturbances, potentially preventing the smooth rebound a model requires. Anisotropy means expansion or contraction proceeds differently in different directions. Imagine a cube of space being squeezed more severely along one axis than another. If such distortions grow too rapidly, the orderly cosmic compression required by a simple bounce may be overwhelmed by a chaotic, lopsided gravitational collapse. This concern has deep roots in relativistic cosmology. The equations of general relativity allow complicated approaches to singular behavior, including rapidly changing directional contractions sometimes described as mixmaster dynamics. Rather than settling into a clean symmetric crunch, space-time can become increasingly irregular. Any convincing bounce model must show why its proposed quantum effects become important before this disorder destroys the conditions needed for a controlled reversal. Quantum effects must become strong enough to halt collapse without generating instabilities that erase the conditions needed afterward. Whether information crosses the bounce predictably also matters, because later observations might retain traces of earlier conditions or lose them completely. If every detail is erased, the pre-bounce phase becomes difficult to test. If some correlations survive, then ancient physics might be written faintly into the pattern of later cosmic structure. Advocates seek models whose equations remain controlled through the extreme regime, rather than relying upon approximations after they have failed. Critics ask whether proposed corrections are derived from complete quantum gravity or inserted phenomenologically to produce the desired reversal. The question is not whether a bounce can be imagined. The question is whether nature permits one under consistent laws, with no hidden instability waiting behind the mathematical simplicity. Entropy presents another obstacle. The observed universe began in an exceptionally low gravitational entropy condition, enabling a long arrow of time. Early matter was hot and nearly uniform, But uniformity is not maximum disorder once gravity becomes important. Gravity tends to clump matter into stars, galaxies, and black holes. The smooth early universe therefore represents a highly special arrangement, despite its apparent thermal simplicity. A contracting predecessor might already contain enormous disorder, black holes, structure, and radiation accumulated through earlier cosmic evolution. Reversing expansion does not automatically reverse entropy. The second law normally drives accessible systems toward more probable and disordered macroscopic conditions. A movie of cream mixing into coffee does not become plausible simply because the film is played backward. Likewise, a contracting universe does not naturally recover the remarkable order needed for a new smooth beginning. Most bounce models therefore need special conditions, mechanisms for dilution, or carefully specified variables that remain orderly through contraction. Some scenarios use a slow phase of contraction dominated by a particular energy component, which can suppress certain distortions before the bounce. Others propose that only selected degrees of freedom carry meaningful information across the transition. Every proposal must confront the same uncomfortable question: where did the low entropy conditions needed for the next cosmic era come from? Any explanation that merely moves the low entropy problem into an earlier phase has postponed the deepest puzzle rather than solved it. These concerns do not invalidate bounce research. They define the hard requirements that distinguish scientific alternatives from attractive cosmological metaphors. A successful model must do more than avoid infinity. It must produce a universe compatible with what telescopes observe, including its smoothness, structure, elemental composition, and long thermodynamic direction. A leading approach comes from loop quantum cosmology, inspired by loop quantum gravity's attempt to quantize spacetime geometry itself. Loop quantum gravity emerged from efforts to apply quantum principles directly to Einstein's geometric description of gravitation. Instead of assuming that space is an infinitely divisible background, it asks whether geometry possesses quantum degrees of freedom. In this view, space may have an underlying granular structure, although not one resembling ordinary grains of sand. Loop quantum gravity suggests that areas and volumes may have discrete quantum structure, rather than varying continuously without limit. The relevant units would be unimaginably smaller than atoms, far beneath any scale current experiments can resolve. They are not tiny cubes floating inside space. Rather, they are proposed quantum properties from which familiar spatial geometry may emerge at large scales, much as a smooth ocean emerges from countless moving molecules. In simplified cosmological models, this discreteness changes gravitational dynamics when density approaches a critical quantum scale near the classical singularity. Areas cannot shrink through arbitrary values in the same classical manner if geometry possesses underlying quantum units and relational constraints. Rather than endlessly intensifying attraction, quantum geometric effects can act effectively repulsively under the most compressed conditions within certain calculations. At that point, contraction can slow, halt, and become expansion. The singularity is replaced by a bounce in the mathematical model. Calculations often show bounded density and curvature where classical relativity predicts divergence, giving a concrete illustration of how singularities might be avoided. The image is dramatic. Instead of a graph shooting upward toward an unreachable infinity, density rises to a maximum, pauses at a quantum threshold, and then descends as expansion resumes. The universe survives its own compression without passing through a point of infinite destruction. This result is important because it emerges from a proposed quantization of geometry, not merely from adding an arbitrary repulsive substance. However, loop quantum cosmology uses symmetry-reduced models, treating the universe as highly uniform while simplifying the full complexities of quantum geometry. This is scientifically useful, but it also creates caution. The real universe contains fluctuations, fields, particles, gravitational waves, and structures that a perfectly uniform model deliberately sets aside. Different choices of quantization, matter content, and initial quantum states can alter details of the predicted bounce significantly. Even if a bounce occurs in the equations, connecting it to our specific observable universe requires a complete cosmological history. Researchers must explain how familiar particles, radiation, large-scale smoothness, and primordial fluctuations emerge after the quantum gravitational transition. They must recover general relativity at ordinary scales while predicting subtle signatures unavailable to purely classical descriptions. Those primordial fluctuations matter because they became the seeds of cosmic structure, Slight density differences in the early universe were later amplified by gravity, eventually forming galaxies and clusters. The microwave background preserves a delicate map of those early variations. Any bounce model must account for their statistical pattern with at least the precision achieved by successful inflationary models. Thus, loop quantum cosmology offers a serious possible mechanism, not an established record of what happened before our hot Big Bang. Other alternatives seek a pre-Big Bang phase through higher dimensional physics, where our visible universe is part of larger structures. Ekpyrotic and cyclic scenarios developed partly from ideas in string theory, including extended objects called branes existing within additional dimensions. A brane can be imagined, imperfectly, as a surface embedded within a larger dimensional setting. Our observable universe might be associated with such a structure, while dimensions beyond direct perception influence its deepest behavior. The name ekpyrotic comes from an ancient Greek term associated with cosmic fire and renewal. Modern ekpyrotic models are mathematical proposals, not revivals of ancient cosmology. They propose that cosmic evolution may include slow contraction, approach, collision, separation, or repeated renewal across immense intervals of cosmic history. A brane collision can be interpreted as releasing energy that initiates conditions resembling a hot Big Bang within our observable dimensions. In these models, the apparent beginning may mark an encounter or transition, rather than creation of all space, matter, and time. Visualized dramatically, two immense sheets drift through a hidden higher dimensional arena, approaching across intervals too large for ordinary language. Their encounter would not resemble two solid objects crashing in a room. It would be a change in fundamental fields and geometry, releasing energy into the dimensions that become our observable cosmos. Their contracting phase can sometimes smooth the universe differently from inflation, suppressing certain irregularities before the hot phase begins. In particular, slow contraction with a sufficiently stiff effective energy component can reduce troublesome anisotropies relative to the dominant background. That is one reason these models attracted serious attention. They attempt to solve a genuine dynamical problem, rather than simply replacing a singularity with a poetic cycle of destruction and rebirth. Cyclic versions extend this idea. Expansion, cooling, contraction, and renewal may repeat, potentially producing many cosmic eras called cycles. Each cycle must preserve enough order to begin again while avoiding destructive accumulation from preceding epochs. The attraction is philosophical as well as physical. A recurrent cosmos appears to evade a unique first event, replacing a single origin with an immense rhythm of transformation. Yet repeated history does not automatically erase origins. It raises questions about whether cycles extend indefinitely, how they began, and why their laws persist. A cycle can be infinite toward the future while still possessing a past boundary. It can also repeat only under special conditions that themselves demand explanation. The word eternal may describe duration, but it does not automatically explain the framework capable of sustaining duration. Entropy remains central because every cycle produces irreversible processes, stars, black holes, radiation, and thermodynamic disorder across its long duration. Proponents propose dilution during immense expansion, or mechanisms that reset relevant conditions before a new contraction and bounce occurs. Critics question whether those mechanisms work in fully realistic settings, remain stable against fluctuations, or simply require finely tuned starting assumptions. The details matter because the second law cannot be dismissed by giving the universe a more elaborate storyline. Any cyclic model must also reproduce the observed nearly scale-invariant primordial fluctuation spectrum and the universe's measured composition with precision. This is a demanding benchmark. Cosmology is not judged only by broad visual resemblance to the universe. It is judged by numerical predictions, the distribution of microwave background fluctuations, the abundance of light nuclei, the growth of galaxies, and the geometry inferred from many independent observations. Penrose offers a strikingly different cyclic proposal called conformal cyclic cosmology, linking the remote future of one cosmic aeon to another. His idea begins with the observation that an extremely expanded future may lose meaningful scales if massive particles eventually disappear. Black holes might evaporate over fantastically long periods, while matter becomes increasingly sparse. What remains could be a cold, dilute universe dominated by massless radiation and the stretched remnants of earlier history. In that limit, a universe with no relevant mass scale can be mathematically rescaled to resemble a new beginning. The far future of one aeon becomes conformally connected to the hot initial state of the next aeon. Conformal transformations preserve angles and causal relationships while changing overall scales. A vast and nearly empty future can therefore be represented in a form that connects mathematically with an extremely compressed cosmic beginning. Penrose does not describe ordinary collapse followed by a conventional bounce through maximum density and quantum repulsion. Instead, he proposes that the end of one cosmic history can be reinterpreted as another history's beginning. The contrast is profound. A conventional bounce turns contraction into expansion. Conformal cyclic cosmology links expansion's ultimate fading future to a fresh hot era through a change of mathematical description. Supporters have searched cosmic microwave background maps for unusual circular patterns or other imprints attributed to energetic events from previous eons. Such patterns, if genuinely predicted beforehand and robustly observed, could offer a rare observational bridge across an otherwise inaccessible cosmic boundary. Claimed signals remain disputed, however, with independent analyses questioning their statistical significance, interpretation, and distinction from ordinary fluctuations or data artifacts. These debates illustrate the proper standard. An imaginative cosmology becomes stronger only when it risks specific observational failure. Patterns found after searching vast datasets require particular caution, because human attention is skilled at finding apparent order in noise. Current microwave background data have not established conformal cyclic cosmology, though continued analysis can refine its predictions and challenges. Thus, cosmic cycles remain possibilities, not evidence that the universe has already lived through earlier complete histories. Inflation opens another route beyond a singular beginning, but it describes accelerated expansion rather than contraction or repeated cosmic renewal. In earlier chapters, inflation helped explain smoothness, flatness, and the primordial seeds of galaxies within our observable cosmic region. During inflation, space expands so rapidly that regions once close together can be driven far apart. Quantum fluctuations are stretched to cosmic scales, later becoming the faint density variations seen in the microwave background. Some versions lead naturally to eternal inflation, where accelerated expansion ends locally, but continues elsewhere across an ever-growing background. Regions where inflation ends become bubble universes, each beginning a hot expanding history with its own local conditions and contents. This process can generate an immense collection of causally separated domains, perhaps infinitely many, without requiring simultaneous endings everywhere. Our observable universe could be one bubble, with its visible Big Bang representing a local transition rather than total cosmic origin. A visual map of eternal inflation resembles a dark, expanding ocean dotted with glowing bubbles, each one growing after inflation ends within it. Yet the metaphor is limited. The bubbles are not necessarily spheres floating through ordinary space, and the surrounding inflating region is not an empty external room. The geometry is dynamical, the distances grow rapidly, and many regions may be forever prevented from communicating with one another. Eternal inflation therefore transforms the question. Instead of one universe emerging once, it pictures ongoing production of many expanding regions. The larger inflating environment may remain inaccessible forever, because light and information from distant bubbles cannot reach our horizon. This makes eternal inflation both explanatory and frustrating. It can broaden the setting while placing much of that setting beyond direct observation, where its claims become difficult to separate from equally coherent alternatives. Yet eternal inflation does not necessarily provide an infinite past. The Bordguth-Vilenkin result remains an important constraint on many inflationary histories. It shows that spacetimes with positive average expansion along certain past-directed geodesics are past incomplete under broad conditions. A geodesic is the closest relativistic equivalent to an unforced path through spacetime. Past incompleteness means that some such paths cannot be extended indefinitely backward within the description being used. The theorem does not depend upon a detailed inflationary potential, conventional energy conditions, or a specific account of quantum gravity. It identifies a boundary or limitation, not a complete story of what lies beyond it. That boundary could involve a singularity, a quantum transition, a bouncing phase, a timeless regime, or some still unknown structure. The result is powerful precisely because it is limited in what it claims. It therefore cannot prove that the universe emerged from literal nothing, Despite claims that sometimes extend its conclusion beyond physics, Bordguth-Vilenkin constrains sustained expansion. It does not uniquely identify what replaces the past boundary or establish an absolute beginning. The theorem may apply to many eternally inflating models, while leaving room for a prior phase governed by different physics. A boundary in a map is not automatically the edge of reality. Multiverse scenarios add another layer. Different bubbles might realize different vacuum states, particle properties, dimensions, or values of fundamental constants. This possibility arises because high-energy theories can contain many metastable configurations, each producing distinct low-energy physical laws locally. A vacuum in this context does not mean empty nothingness. It means a lowest energy state of fields, still governed by laws and capable of possessing structure. Observers would then find themselves only where conditions permit stable matter, complex chemistry, long-lived stars, and perhaps life. Anthropic reasoning states this selection effect plainly. We should not be surprised to observe a universe compatible with observers, because incompatible regions contain no observers available to notice them. This reasoning can sound circular, but it identifies a real constraint on what any observer can ever report. Selection can explain why observed conditions appear unusual within a larger ensemble, but it does not show how that ensemble originated. It also cannot by itself derive a unique value for every constant or replace dynamical accounts of cosmic history. A multiverse may explain why our location is habitable without explaining why laws, possibilities, inflation, or bubble formation exist at all. If anything, it expands the original question. Why does reality contain a landscape capable of generating different physical worlds? The measure problem makes multiverse reasoning technically difficult. In an infinite or eternally growing collection, every allowed type of universe may occur endlessly many times. To calculate probabilities, researchers must decide how to compare infinities. Should bubbles be counted by volume, by time, by observers, by causal regions, or by some deeper quantum prescription? Different choices can yield different predictions for what a typical observer should see. Without a justified measure, probabilities can depend on how regions are counted, ordered, or cut off at arbitrarily chosen stages. The same theory may predict different typical observations under different counting procedures, weakening claims of clear observational confirmation. Critics argue that this ambiguity threatens falsifiability. Supporters reply that measures may emerge from deeper theory or become constrained by consistency with precise observations. Therefore, the multiverse is not one claim, but a family of proposals requiring defined dynamics, probability rules, and observational consequences. Testing these ideas remains difficult, but difficulty does not mean every proposal lies beyond science, or every proposed signature carries equal weight. Spatial curvature offers one possible clue. A measurable departure from flatness could constrain inflation, certain bounces, or geometry inherited from earlier phases. Current observations indicate that the observable universe is very close to spatially flat, but even a small confirmed deviation would carry important information about its earliest evolution. Detecting distinctive patterns in cosmic microwave background fluctuations could reveal unusual primordial correlations, suppressed power, or evidence of pre-inflationary dynamics. The microwave background is especially valuable because it preserves information from an early transparent universe, released when electrons and nuclei first combined into neutral atoms. Across the sky, its tiny temperature variations form a fossil image of conditions nearly 14 billion years ago. Primordial gravitational waves could probe extremely high-energy physics, distinguishing some inflationary scenarios and perhaps constraining alternatives with contracting phases. These would be ripples in space-time generated in the early universe, not the later waves produced by colliding black holes. Their most sought-after imprint is a subtle pattern in the polarization of microwave background light. Detecting that signal securely would transform the evidence available for competing accounts of the earliest cosmic era. Large-scale anomalies invite attention, but anomalies are not automatically messages from another aeon, bubble collision, or cosmic bounce. They can arise from chance, incomplete data, foreground contamination, instrument limitations, or statistical choices made after patterns are noticed. Yet predictions of bubble collisions sometimes include localized microwave background features, while some bounce models predict altered correlations at the larger scales. The challenge is to distinguish a genuine forecast from a flexible explanation, constructed after the data appear. Cosmic horizons impose a fundamental limit. We observe only regions whose signals have had time to reach us since the early universe. A neighbouring bubble might leave a detectable collision signature, but most hypothetical domains could remain permanently outside causal contact. The horizon is not merely a technological barrier. Even a perfect telescope cannot receive light or information that the structure of space-time prevents from ever arriving. Scientific humility is required here. A theory may be mathematically coherent and still lack accessible evidence capable of separating it from rivals. The goal is not to demand immediate laboratory replication of the universe's first extreme conditions. The goal is to derive constrained consequences that could fail through astronomical observation, internal inconsistency, or conflict with established physics. Mystery is not evidence, and mathematical possibility is not historical confirmation. No current bounce, cyclic model, conformal aeon, or multiverse scenario has displaced the standard hot Big Bang account of observable history. They address what might lie beyond its earliest tested domain, where general relativity and quantum theory remain incomplete together. Their value lies partly in exposing assumptions. A singularity need not be a physical beginning, inflation need not be a total origin, and quantum language need not mean nothing. We have moved from asking what happened before the bang toward a harder question about what would count as explanation. A physical explanation usually relates phenomena through laws, states, symmetries, and mathematical structures that are already available for description. But when the object being explained is the totality of physical reality, those explanatory resources become part of the mystery themselves. The laws doing the explaining are no longer safely outside the question. A bounce explains expansion through contraction only if space-time, quantum geometry, and dynamical laws already have meaningful roles in the deeper account. A cycle explains one aeon through another only if recurrence, entropy, and the structures enabling renewal are physically justified across every transition. A multiverse explains local conditions through selection only if its larger landscape, probability measure, and universe-producing dynamics can be independently specified. Each proposal reaches beyond the hot Big Bang, but each carries assumptions into that deeper darkness. None of these observations dismisses cosmology. They show why its frontier must join technical precision with philosophical clarity about assumptions and scope. The Big Bang remains strongly supported as the beginning of our observable, hot, expanding cosmic history, not necessarily the beginning of every reality. Science has not shown that absolute nothing created everything, because absolute nothing contains no laws, fields, time, potential, or transition. It has shown that space, time, causation, vacuum, and perhaps even cosmic beginnings may be emergent concepts rather than permanent foundations. That possibility is both unsettling and fertile. The categories used to ask the oldest question may be products of the universe's later, calmer conditions. If so, the final answer may not resemble an earlier event hidden behind the bang, but a deeper account of why events, laws, and time can exist at all. The next question is not simply which story sounds most satisfying, it is which explanation genuinely explains and what it must assume. Beyond the observable horizon, models multiply. Beneath them all, the original silence remains, asking why there is a reality capable of becoming anything. The question returns after every model reaches its deepest boundary, because nothing has never meant one thing alone. Sometimes nothing means empty space, a vast geometry containing distance, duration, fields, and possible events already within it. Sometimes it means no particles, while quantum fields, vacuum states, laws, and space-time remain fully present beneath appearances. Sometimes it means no classical space-time, a condition invoked by quantum cosmology, without necessarily removing mathematical structure entirely. Sometimes it means no prior time, although equations, possibilities, amplitudes, and relations may still organize proposed cosmic histories. Only absolute non-being means no space, time, fields, particles, laws, mathematics, potential, relation, or possibility whatsoever remains. This distinction is more than a technical footnote, because each version of nothing carries a different burden of explanation. An empty room is not nothing, because it contains volume, dimensions, gravity, air, and the possibility of entering it. Intergalactic space can look black and silent, yet it remains threaded by radiation, quantum fields, curvature, and distant gravitational influence. Even a universe stripped of particles might retain a stage on which particles could later appear. Absolute non-being permits no stage, no potential audience, no waiting interval, and no rule by which a change might occur. It cannot be dark, because darkness is already a condition, experienced within space and time. It cannot be silent, because silence still implies duration and the absence of sound against a possible background. The language falters here, and that failure is itself part of the mystery. Arguments about cosmic origins often conflict because speakers cross these definitions without acknowledging their change in meaning. A vacuum can fluctuate because quantum theory defines a vacuum, fields define states, and time defines evolution. Empty space can expand because geometry exists, physical laws operate, and distances can change between separated locations. A tunneling universe can appear only where quantum amplitudes, possible configurations, and a governing formalism already have meaning. A bounce can occur only where a deeper system possesses states, dynamics, and conditions capable of reversing collapse. None of those claims is trivial, and each may describe reality near the earliest accessible cosmic threshold. But none automatically answers the older question hidden beneath scientific language about why any framework exists at all. That question was given its most famous formulation by the philosopher Gottfried Wilhelm Leibniz, centuries before modern cosmology. Why is there something rather than nothing, Leibniz asked, when nothing might seem simpler than every existing thing? He wrote during an age when celestial motion was increasingly understood through mathematics. Yet the existence of an ordered cosmos still appeared astonishing. For Leibniz, the question was not merely about the first physical event. It concerned why there is any reality capable of containing events, truths, substances, or mathematical order. His formulation survived because scientific success did not make it disappear. In some ways, every successful explanation made the question sharper by revealing still deeper layers of structure beneath familiar appearances. The question remains powerful because physical explanations usually begin by assuming something structured enough to explain anything else. A theory may explain galaxies through gravity, gravity through geometry, and geometry through deeper quantum principles. Yet each further layer can leave open why there are principles, structures, or possibilities capable of supporting explanation. Leibniz connected this unease with the principle of sufficient reason, the intuition that every fact requires explanation. According to that intuition, reality cannot simply be an unexplained remainder, suspended beyond every possible reason or cause. If the universe exists, perhaps there must be a reason why it exists rather than failing entirely. If laws have their particular form, perhaps some deeper necessity, logic, or explanation must determine that form. If initial conditions were special, perhaps they too require an account rather than appearing as arbitrary cosmic givens. The principle is compelling because ordinary science succeeds by seeking reasons behind patterns that initially seem mysterious. Planetary motion once seemed celestial fact, until gravity connected it with falling objects and mathematical regularity on Earth. Atomic spectra seemed disconnected lines, until quantum theory linked them to quantized energy and microscopic physical structure. Cosmic expansion seemed surprising, until general relativity and observations revealed an evolving geometry on the larger scales. Scientific progress repeatedly converts apparent brute facts into consequences of deeper, more unified descriptions and testable relationships. The history of physics gives that expectation emotional force. Newton did not merely calculate planetary paths, he linked the moon's orbit to an apple's fall through one universal law. Maxwell united electricity, magnetism, and light within a common field theory, transforming separate phenomena into aspects of one structure. Einstein then replaced gravity as a force with curved spacetime, showing that geometry itself could become dynamical. Such unifications teach us to suspect that apparent arbitrariness may conceal a deeper principle. Yet they also teach caution, because each unification begins with equations, symmetries, and conceptual rules not generated by the explanation itself. But success within nature does not prove that nature itself must possess a further explanation beyond every level. Perhaps some laws are brute facts, true without deeper cause, even if their consequences remain precisely describable experimentally. Perhaps a quantum event can be fundamentally probabilistic, governed statistically without a hidden fact selecting its particular outcome. Perhaps existence is not the kind of fact that can be explained through an earlier cause. Those possibilities do not end inquiry, but they challenge the assumption that explanation must continue indefinitely downward. A brute fact is not nonsense, nor is it a satisfying conclusion for minds trained to search. It is a possible stopping point, where reality simply is a certain way without deeper justification. This possibility can feel intellectually unsettling, because it denies the familiar promise of a final reason. Yet every chain of explanation must either continue without end, close upon itself, arrive at necessity, or terminate in something unexplained. An infinite regress may preserve the demand for a reason at every local step, while leaving the whole sequence without a foundation. A circular explanation may describe mutual dependence, but it can seem unable to explain why the circle exists. Necessity may offer a stronger answer if reality could not have been otherwise. Brute fact accepts the opposite possibility. Perhaps the deepest layer is simply there, without hidden machinery below it. The tension between sufficient reason and brute fact cannot be settled merely by choosing the emotionally preferable answer. It requires clarity about what kind of explanation is being requested and what resources an explanation can use. Causes ordinarily connect events within time, linking earlier conditions to later outcomes through regular physical processes. Yet time itself may be part of the reality whose origin or emergence we are attempting to understand. A cause before time risks importing the very temporal framework that the question asks us to explain. A law outside reality risks treating laws as objects existing independently from the world they govern. A mathematical explanation may show internal necessity while leaving unanswered why mathematics describes concrete physical existence successfully. The mystery therefore sharpens when ordinary explanatory tools are turned toward the totality containing those tools themselves. At this boundary, science does not surrender rigor, but it must identify where rigor reaches conceptual limits. The difficulty resembles trying to stand outside a map in order to map the entire territory, including the place where the mapmaker stands. We can extend our models toward earlier and more extreme conditions, but each model is formulated from within a language of relations. Even the question of an external viewpoint may be misleading, because there may be no outside to physical reality. The universe is not an object resting inside a larger room, waiting for an external cause to act upon it. The word law becomes central, because every origin proposal seems to rely upon laws before explaining their status. Are physical laws prescriptive rules that somehow command matter, energy, and geometry to behave in particular ways? That image is vivid, but it suggests a legislator, an enforcement mechanism, and entities already available to obey. Perhaps laws are descriptive summaries, concise human statements of regularities observed throughout the physical world instead. On that view, laws do not govern reality from outside, but report stable patterns reality displays. Yet descriptions raise another question, because why should nature exhibit deep, elegant, and mathematically stable regularities at all? A law of physics is unlike a law passed by a government. No cosmic officer appears to enforce conservation of energy, and no particle receives instructions before interacting with another. Instead, physical laws are expressed as relationships that hold, with astonishing reliability across distances, epochs, and experimental settings. The same electromagnetic equations that describe a laboratory laser also govern radiation from ancient galaxies. The same quantum principles that shape atoms in human bodies operate within the hot plasma of the early cosmos. This universality is so familiar that it can seem ordinary. It is not ordinary. It is one of the deepest observed facts about reality. Some physicists regard laws as timeless relations, not commands or summaries, embedded within a fundamental mathematical structure. Others suspect familiar laws emerge only approximately, like temperature emerging from countless molecular motions within ordinary matter. Temperature is real and measurable, yet it is not a primitive ingredient in descriptions of individual particles. A gas has temperature because enormous numbers of molecules collectively distribute energy in a recognizable statistical pattern. At a sufficiently microscopic level, the smooth concept dissolves into individual collisions, velocities, and probabilities. Perhaps space-time, particles, fields, and even laws are similarly emergent patterns within some deeper quantum reality. If so, asking what laws existed before the universe may misuse language inherited from later cosmic conditions. The deepest framework might not contain laws in the familiar textbook sense, only relations from which law-like behavior arises, Or perhaps laws are necessary, holding in every possible reality because their denial would produce contradiction or incoherence. That proposal shifts the question toward logic itself, asking why logical necessity has any connection with existence. Why should a reality that exists at all be intelligible through structures that minds can formulate? And why should consistency, rather than contradiction or complete absence, have any claim upon what is physically real? Mathematics makes this shift especially provocative, because physical theories are written in mathematical forms of extraordinary precision. Equations predict eclipses, particle collisions, gravitational waves, atomic transitions, and cosmic expansion with remarkable quantitative success. This effectiveness encourages the thought that mathematics may not merely describe reality, but constitute its deepest foundation. Perhaps the universe is a mathematical structure, and physical existence means belonging to a consistent mathematical pattern. The proposal is radical because mathematics seems abstract, timeless, and independent of the particular material objects we encounter. Numbers do not appear to age, decay, collide, or occupy locations the way particles and planets do. A triangle theorem seems true regardless of whether triangles are drawn, imagined, or physically instantiated anywhere in nature. The strange effectiveness of mathematics has impressed thinkers since antiquity, although modern physics made the puzzle unusually vivid. A few symbols on a page can predict a planet's position years ahead, describe an electron's interference pattern, or calculate the faint stretching of spacetime from colliding black holes. In observatories, this abstraction becomes visible as data points, spectral lines, and arcs of light bent by gravity. Mathematical structures seem to reach into nature with almost uncanny precision. Still, a successful equation may be a language of description rather than the substance of what it describes. The distinction remains difficult to erase, but mathematical consistency alone may not explain why one structure is physically actual rather than merely conceivable. There are infinitely many mathematical systems, including systems unlike the observed universe in their dimensions, symmetries, and laws. Does every consistent structure exist physically, as some proposals suggest? Or does physical existence require an additional principle? If every structure exists, what distinguishes actual existence from mathematical possibility, and what makes observation meaningful within it? If only some structures exist, what selects them? And does selection require laws more fundamental than those selected? Mathematics can organize possibilities with unmatched power, but possibility is not obviously the same as concrete reality. A map can represent terrain precisely without producing mountains, rivers, or the physical ground beneath its symbols. Likewise, an equation can describe a universe without obviously explaining why that universe is instantiated physically. A musical score contains relationships among notes, yet it does not by itself produce air vibrations in a concert hall. The analogy is incomplete, because mathematical realism may assign numbers a deeper status than a score possesses. Even so, it identifies the unresolved step between formal structure and lived physical fact. The mathematical universe idea exposes a profound divide between describing existence and accounting for existence itself. It also reveals how quickly familiar words become unstable when applied beyond ordinary physical settings. Symmetry offers another route that can seem to make something arise naturally from apparent nothing. In physics, a symmetric state can contain no preferred direction, location, particle, or visible structure initially. Yet symmetry does not mean absence of properties, equations, energy, or possible changes within a defined system. A perfectly balanced pencil can fall, but its instability belongs to a world containing gravity, matter, space, and time. A supercooled liquid can transform, but its transformation requires molecular interactions and thermodynamic conditions already present. A quantum field can occupy an unstable state, and later settle into a richer configuration with particles or forces. In the early universe, symmetry breaking may have helped distinguish forces that were once unified at extreme energies. As the cosmos expanded and cooled, fields could settle into new configurations, much as cooling water forms ice with a distinct internal order. The image is not of creation from emptiness, but of phase change within an already existing physical system. A smooth field can acquire a non-zero value everywhere, changing which particles are massive and how forces operate. Minute quantum variations can then be stretched across cosmic distances, becoming seeds for later galaxies. What appears visually empty may therefore conceal immense latent structure, but latent structure is not nothing. Such symmetry breaking helps explain how uniform beginnings can develop differentiated structures, including distinct forces and cosmic patterns. It is scientifically important because apparent simplicity can conceal a capacity for dramatic physical transformation under small disturbances, but instability never creates its own stage, its own equations, or the physical system whose balance becomes unstable. An unstable vacuum is still a vacuum state of fields governed by a theory. A false vacuum is not philosophical nothing because it possesses energy, structure, and possible transitions. A symmetric quantum state is not non-being because symmetry is already a property with mathematical and physical content. The distinction matters most when cosmic language compresses technical claims into dramatic claims about creation from nothing. Physics can show how sparse or balanced conditions evolve into complexity without showing how absolute non-being becomes possible. That achievement is still immense, because explaining transformation is different from merely naming the transformed result. The scientific mystery becomes more precise when attention returns to the early universe's extraordinarily low gravitational entropy. The first hot cosmic state was not simply empty, dark, or featureless in the ordinary sense. It was a hot plasma, nearly uniform across enormous distances, filled with radiation, particles, and expanding space-time. Yet smoothness is deeply special once gravity matters, because gravity naturally amplifies clumping rather than preserving uniform distributions. Later cosmic history displays that tendency through stars, galaxies, clusters, and black holes, forming from tiny primordial variations. Black holes carry enormous entropy, suggesting that a highly clumped gravitational state can be vastly more probable than smoothness. This is counterintuitive because a smooth gas in an ordinary box often seems more disordered than a clumped one. Gravity reverses the intuition on cosmic scales. When matter gathers, gravitational attraction creates more ways for energy and matter to be arranged, especially as dense objects radiate heat outward. A collapsing cloud can form stars while increasing total entropy, and a black hole represents an extreme concentration of gravitational entropy. The early universe, by contrast, resembled an almost uniform glowing sea. Its remarkable smoothness was not a generic equilibrium condition, but an extraordinarily constrained starting arrangement. The early universe began far from such gravitational equilibrium, in a remarkably ordered state despite its high temperature. This special beginning gave the universe an arrow of time, allowing entropy to increase through structure, chemistry, life, memory, and history. Without low initial gravitational entropy, familiar distinctions between past and future might never have emerged in stable form. Broken eggs would not remain broken in a meaningful statistical direction, stars would not steadily shine, and records of earlier events would lack a physical basis. The arrow of time is therefore not merely a feature of clocks, it is written into the universe's unusual initial condition, then carried forward through every irreversible process we observe. The question is therefore not merely why there was a void before matter appeared, it is why the early cosmos occupied a condition so extraordinarily special among its possible gravitational arrangements. Inflation may explain aspects of smoothness, flatness, and primordial fluctuations, depending on its starting conditions and underlying physics. During inflation, space may have expanded at a tremendous rate, stretching microscopic regions into a vast and nearly uniform cosmic domain. But inflation itself requires a state, a field or mechanism, and conditions allowing accelerated expansion to begin. Bounce models face the same challenge because they must explain how a prior contraction produces suitable order afterward. Multiverse proposals may distribute different beginnings across many regions, but they still require an ensemble and generating dynamics. Each model can relocate the low entropy question without necessarily dissolving it completely. That is not a defect unique to cosmology, but a measure of how deep the problem reaches. Cosmology nevertheless changes philosophy by forcing vague questions into contact with measurable properties of the actual universe. The universe is not an unrestricted thought experiment, because its geometry, expansion, composition, and relic radiation leave records. Those records arrive as faint microwave photons, gravitational distortions, elemental ratios, and immense maps of galaxies. They are traces from an ancient epoch, carried across billions of years into telescopes, detectors, and carefully calibrated instruments on a small planet orbiting an ordinary star. Measurements of cosmic curvature test whether space is nearly flat, positively curved, negatively curved, or evolving beyond simple assumptions. Expansion history traces how cosmic growth changed from radiation domination through matter domination into present accelerated expansion. Particle properties constrain early conditions, including neutrino masses, dark matter behavior, and the number of light particle species. Microwave background maps preserve primordial fluctuations, providing detailed statistical tests for inflation, bounces, and alternative early histories. Across those maps, temperature differences of only millionths of a degree reveal the faint pattern from which later structure grew. Primordial gravitational waves could reveal high-energy dynamics through subtle polarization patterns or other cosmic relic signatures. Searches for non-Gaussian fluctuations can test whether primordial perturbations followed the simplest inflationary statistical expectations. Abundances of hydrogen, helium, and other light elements constrain the thermal conditions of the early expanding universe. Large-scale galaxy surveys trace how gravity amplified ancient fluctuations into the cosmic web observed across immense distances today. On these maps, galaxies form luminous filaments around great dark regions, outlining a structure shaped by gravity over billions of years. The visual grandeur is inseparable from the precision, because every filament and statistical correlation can constrain a proposed cosmic past. These observations do not directly photograph a first moment, but they restrict what plausible early histories can be. A proposal that predicts incorrect curvature, wrong fluctuation patterns, or incompatible particle abundances cannot survive on philosophical elegance alone. A theory that offers no distinctive consequences may remain interesting, but it stands farther from empirical confirmation. Observational cosmology thus transforms some origin questions into constrained scientific programs, rather than unrestricted imaginative speculation. It asks what physical processes could produce this universe, with these relics, parameters, and observable regularities. The distinction matters because a beautiful origin story is not automatically a scientific theory. Scientific models must expose themselves to possible failure through predictions that nature can contradict. A slight mismatch in the microwave background spectrum, an absent gravitational signature, or an impossible abundance of light elements can eliminate years of speculation. This discipline does not make cosmology less imaginative. It makes imagination answerable to a universe that existed long before human observers began asking questions. The sky becomes an archive, and physics becomes a method for reading its damaged but persistent pages. It cannot guarantee that every meaningful question becomes measurable simply because it concerns the universe. Methodological science proceeds by defining models, deriving consequences, measuring nature, and revising claims when evidence disagrees. This method is powerful precisely because it limits itself to claims that can be connected to observation. Science can test models of early evolution, even where direct laboratory recreation remains impossible. Science can compare inflationary predictions, bounce signatures, curvature constraints, and gravitational wave backgrounds against increasingly precise data. Science can identify where general relativity fails, where quantum theory becomes indispensable, and where current equations remain incomplete. Science can clarify that a quantum vacuum differs fundamentally from absolute philosophical nothingness, but science may not be equipped to decide why logical possibility obtains, why mathematics applies, or why existence exists. Those questions may be meaningless, answerable through philosophy, answerable through deeper science, or permanently beyond available concepts. Declaring them impossible too quickly would confuse present limits, with proof that no future understanding can emerge. Declaring them solved through one elegant equation would confuse formal success with a final metaphysical verdict. Intellectual humility is not defeat, because uncertainty can mark the boundary between tested knowledge and unsupported assertion. There is a difference between acknowledging a boundary and turning that boundary into a permanent wall. Physics has repeatedly transformed seemingly inaccessible questions into empirical ones. The composition of stars, the age of Earth, the existence of atoms, and the expansion of the universe were once matters of speculation beyond direct reach. New instruments and conceptual breakthroughs made each measurable in unexpected ways. The deepest origin question may eventually be reframed by a theory not yet imagined. or it may remain resistant because it asks for a kind of explanation that no physical observation can supply. Either possibility requires patience rather than premature certainty. We know the observable universe expanded from an early hot, dense state nearly 14 billion years ago. We know its relic radiation, elemental abundances, and large-scale structures strongly support that thermal cosmic history. We do not know whether that history began from a singular event, a quantum transition, a bounce, or something stranger. We do not know whether time extends through a deeper phase, emerges from relations, or begins with our observable history. We do not know whether physical laws are fundamental, emergent, necessary, descriptive, or contingent features of reality. We do not know why the early universe began with its extraordinary gravitational order. We do not know whether a final explanation must exist, or whether some facts are ultimately brute. These admissions are not empty. They define the frontier with greater precision than confident myths ever could. The inability to name a final cause does not erase the progress achieved by cosmology and physics. It reveals where concepts of cause, time, law, and nothingness reach limits shaped by ordinary experience. We evolved within a late universe where events occur in time, objects occupy space, and explanations connect nearby causes. At the deepest cosmic boundary, those categories may be emergent tools rather than eternal features of reality itself. A question can be grammatically well-formed while silently assuming conditions that nature does not fundamentally provide. What happened before the beginning may fail if before requires time, and beginning describes time's emergence. What caused the laws may fail if causation is a relation defined only within law-governed temporal processes. Why did nothing become something may fail if nothing cannot possess potential, transition, or any capacity whatsoever? Yet failure of familiar wording does not make the underlying wonder trivial or disposable. It demands better distinctions, stronger models, and patience with questions that remain larger than current answers. The climax is not a revelation that nothing suddenly produced everything through a known scientific mechanism. The revelation is harsher and more astonishing. Every proposed mechanism begins with some structure, even when that structure is hidden beneath unfamiliar mathematics. A quantum state assumes possibilities, a law assumes regularity, a symmetry assumes a system, an instability assumes properties capable of changing, a vacuum assumes fields, a beginning assumes a way of ordering change. The closer cosmology approaches the earliest boundary, the more visible these assumptions become. That visibility is progress, because hidden assumptions cannot be tested, compared, or honestly distinguished from conclusions. The Big Bang remains strongly supported as the beginning of our observable, hot, expanding cosmic history. It is not established as an explosion of something into a pre-existing empty void. It is not established as proof that absolute nothing created everything through a physical process. It is a threshold beyond which our most familiar categories begin losing their ordinary meanings. Space may not be a container, time may not be an external clock, causation may not extend beyond temporal order, vacuum may not be emptiness. Nothing may be a word whose meanings diverge precisely where the universe becomes most mysterious. The final chapter must gather these distinctions without pretending to close the question prematurely. It will return to the evidence, the models, and the silence behind every assumed framework. The deepest answer may be a future theory, a philosophical necessity, a brute fact, or a limit on explanation. But the question endures because reality exists, and because every answer reveals another condition that made answering possible. At the beginning, we imagined black emptiness surrounding a universe before its first light appeared anywhere at all then. That image is powerful, but it carries assumptions the investigation has spent 8 chapters carefully removing from view. Blackness requires space where light might travel, observers who might see it, and time within which darkness could endure. Outside requires a boundary, a larger arena, and distances extending beyond the thing said to have begun. If space and time emerged with the universe, neither blackness nor outside could have been waiting beforehand. The silence in our opening question was never a confirmed place. It was a name for the limit of ordinary imagination. We pictured an empty stage because human experience always begins with stages, rooms, horizons, clocks, and events. Cosmology has taught us that the stage itself may belong to the story. The question was not foolish, but its familiar wording concealed its deepest difficulty. What could happen after nothing, if nothing contains no time, possibility, change, or conditions for happening? Even the colour black is a physical impression, produced when eyes receive little visible light across a region of space. Before photons, retinas, and directions, the image loses its ordinary meaning. In visual terms, the imagined void often appears as a vast velvet backdrop, yet that backdrop quietly supplies depth, distance, and a viewpoint from which to watch. The correction is more radical than replacing darkness with brightness. It removes the backdrop itself. The secure part of the story is already astonishing. Our observable universe expanded from an early hot, dense state nearly 14 billion years ago. That conclusion rests upon several independent records written across the sky and tested with increasing precision. Distant galaxies show systematic redshift, revealing that large-scale distances grow as spacetime expands between them. The cosmic microwave background preserves relic light from a universe becoming transparent roughly 380,000 years after the hot beginning. Its nearly uniform glow and tiny fluctuations reveal an early plasma with extraordinary regularity and measurable primordial variation. Light element abundances support nuclear reactions expected during the first minutes of rapid cosmic cooling. Hydrogen, helium, and traces of other light nuclei match a thermal history calculated long before modern surveys refined it. Galaxy evolution and large-scale structure show how tiny early variations grew through gravity into stars, galaxies, clusters, and webs. Together, these observations do not merely suggest expansion, they establish a coherent cosmic history that competing explanations must reproduce in detail. The Big Bang is therefore not a speculative metaphor. It is the strongly supported beginning of our observable, hot, expanding cosmic history. Those records arrive through different physical messengers, and their agreement is especially compelling. A galaxy's stretched spectral lines measure expansion, while the microwave background's temperature variations trace density patterns in the primordial plasma. Maps of those variations look almost smooth from afar, yet their faint mottling became a blueprint for later cosmic architecture. Under gravity, slightly denser regions drew in more matter, eventually igniting the first stars and gathering galaxies along filamentary bridges. The evidence is not one ancient photograph. It is a mutually consistent reconstruction. Yet that achievement does not settle what the earliest boundary means. Reversing the equations of general relativity leads toward extreme density, curvature, and temperature, then toward a singular limit. But singularities are warnings that a theory has reached its domain of failure. They are not observed locations where science has watched existence appear from non-existence. General relativity describes gravity and cosmic expansion with extraordinary success, but it treats spacetime classically and continuously. Quantum physics describes matter, fields, and probability with equal success, but it lacks a completed union with gravity. Near the Planck regime, both theories should matter at once. No confirmed quantum gravity theory yet tells us what physically replaces the classical extrapolation. The earliest epoch remains hidden behind equations that become incomplete precisely where the origin question becomes most urgent. We do not know whether the hot beginning followed a prior phase, emerged from timeless quantum relations, or marked time's beginning. We do not know whether the singularity represents a real boundary, a transition, or simply an obsolete mathematical description. At scales near the Planck length, familiar distinctions between geometry and matter may cease to be reliable. Quantum fluctuations of spacetime itself are expected to become important there, although no instrument can directly probe that domain. The classical singularity may therefore resemble a warning light on a map, marking territory where known coordinates no longer guide us. Inflation deepened both the explanatory power and the mystery of early cosmology. A brief period of accelerated expansion can explain broad smoothness, near flatness, and seeds for later cosmic structure. Microwave background measurements strongly support several predictions associated with simple inflationary ideas. But inflation requires an underlying mechanism, an appropriate state, a way to begin, and a process called reheating. Its hypothetical inflaton field has not been directly identified. Its origin remains as much a frontier as the origin of the hot Big Bang itself. Eternal inflation may produce many local hot beginnings, yet many such models remain past incomplete under broad conditions. Past incompleteness identifies a limit in a spacetime description, not proof that literal nothing preceded every physical reality. the low-entropy initial condition presents an equally profound problem. The young universe was hot and nearly uniform, yet gravitational physics makes that smoothness extraordinarily special, rather than generic. That special order gave later history an arrow, allowing stars, chemistry, memory, observers, and every record of a past. Inflation also transforms microscopic uncertainty into a visible cosmic pattern. In many versions, quantum fluctuations were stretched beyond the horizon, then later re-entered as slight density differences. That mechanism elegantly links the subatomic world to the distribution of galaxies, yet elegance is not identification. Researchers still seek distinctive signatures that separate inflation from plausible alternatives. That smooth beginning is visually deceptive. A nearly uniform gas seems ordinary, but gravity amplifies clumps, making smoothness a remarkably constrained condition. The early cosmos contained enormous thermal energy, yet comparatively little gravitational disorder. Why that arrangement prevailed remains one of cosmology's sharpest unanswered questions. Quantum cosmology offers serious possibilities, but its language must be translated with unusual care. Some proposals describe a regime without classical space and time. That does not mean a regime without all structure, laws, amplitudes, relations, or mathematical possibilities. The Huttle-Hawking no-boundary proposal replaces a sharp initial edge with a smooth quantum geometry of finite extent. Vilenkin's tunneling proposal uses nothing to mean no classical spacetime, not absolute philosophical non-being. Wheeler-DeWitt approaches suggest that time may emerge from correlations within a quantum description rather than exist fundamentally. Such ideas are difficult because the universe has no external observer, laboratory clock, or background space assumed outside itself. Yet they are serious attempts to make space-time itself a consequence rather than an unquestioned starting point. They show how classical reality might emerge from a deeper quantum account. They do not show that absolute nothing produced everything. Any quantum account still invokes some formal structure capable of describing states, relations, probabilities, or possible cosmic histories. The phrase quantum state can sound abstract, but it names a structured account of what outcomes are possible and how they are related. It is not a blank page. Even where ordinary time is absent, a proposal must provide amplitudes, constraints, or boundary conditions. The mystery then shifts rather than disappears. Why should any such organizing principle obtain at all? Other models ask whether the hot Big Bang was a transition rather than a first event. A bounce proposes an earlier contraction that reached a finite quantum regime, reversed, and became our expansion. Loop quantum cosmology offers one mathematical route, where quantum geometry may prevent density and curvature from becoming infinite. Cyclic and ekpyrotic proposals imagine repeated eras, sometimes involving contraction, renewal, or higher dimensional interactions beyond familiar spacetime. Conformal cyclic cosmology connects the remote future of one aeon with another hot beginning through a distinctive mathematical transformation. Eternal inflation imagines local bubble universes forming within an accelerating larger process. Each possibility challenges the simplest picture of a single cosmic beginning. None has one decisive observational confirmation. Bounces must control instabilities, preserve or explain primordial fluctuations, and confront the immense problem of low initial entropy. Cycles must explain why recurrence remains stable and why disorder does not accumulate destructively across successive eras. Multiverse models must specify dynamics, probability measures, and testable consequences despite horizons that may permanently block direct observation. Every alternative must reproduce the microwave background, elemental abundances, cosmic geometry, and galaxy structure already explained by the standard history. Observationally, the challenge is severe because later cosmic evolution can erase delicate traces of an earlier phase. Researchers therefore search for residual fingerprints in microwave polarization, primordial gravitational waves, and statistical features that depart from the simplest predictions. A confirmed anomaly would not instantly reveal its cause, but it could narrow the field of viable histories. Thus, the central question changes shape once again. We no longer ask only what happened before the bang. We ask what would count as an explanation when space, time, causation, and law may themselves require explanation. If the universe had a finite beginning, what could cause it when causes usually connect earlier events with later ones? A cause without time may be a meaningful, deeper relation, or it may misuse language built for ordinary temporal experience. If the universe did not begin, how can an eternal cosmos avoid an origin or reinterpret what origin means? Infinite duration does not automatically explain why an enduring framework exists. A chain of prior events can stretch indefinitely, while still leaving its laws, order, and possibility unexplained. If physical laws are fundamental, why those laws rather than others? If laws emerge, what deeper reality allows law-like behavior to emerge? If all consistent mathematical structures exist, what distinguishes physical actuality from abstract possibility? Each answer opens another layer because the tools used for explanation become part of what demands explanation. This is where science and philosophy meet without becoming interchangeable. Science tests models by deriving consequences and comparing them against the physical universe. It can reject an early history that predicts the wrong abundance of helium, incorrect microwave fluctuations, or impossible cosmic geometry. It can constrain inflation, test alternatives, and identify where present theories become incomplete. It can distinguish a quantum vacuum from literal absence. Philosophy clarifies what follows and what does not follow from those successful scientific descriptions. It asks whether explanation must end in necessity, brute fact, infinite regress, or a kind of question beyond familiar categories. Neither discipline is strengthened by claiming more than its methods can justify. Mystery is not evidence for any preferred answer. Mathematical possibility is not historical confirmation. A beautiful origin story becomes science only when it risks disagreement with nature. A philosophical conclusion becomes clearer when it does not disguise assumptions as discoveries. Humility is not surrender before ignorance. It is the discipline of separating measured knowledge from tempting language at the frontier. That standard matters because origin language can become seductive precisely where evidence is thin. A model earns attention not by answering every metaphysical desire, but by surviving quantitative comparison with the sky. The discipline can feel austere. It is also what keeps wonder connected to reality. We should therefore answer the title carefully, and without reducing its force. No confirmed scientific theory demonstrates that absolute philosophical nothing started the Big Bang. Absolute nothing would contain no space, time, fields, particles, laws, vacuum states, mathematics, potential, or transition. It could not fluctuate, tunnel, decay, wait, or create, because each verb assumes some structure already exists. The quantum vacuum is not nothing. It contains fields, measurable effects, physical states, and laws governing their behavior. Empty space is not nothing. It contains geometry, duration, causal relations, and possible motion. A universe without classical space-time may still not be nothing if a quantum framework organizes its possible emergence. When physicists use nothing in technical proposals, they often mean something far stranger than everyday emptiness. That distinction does not diminish those proposals. It protects their actual achievements from exaggerated claims. Physics may explain how one structured condition becomes another. It has not established a physical process by which absolute non-being becomes being. The conclusion is therefore neither a simple creation story nor an admission that cosmology has learned nothing. We have learned that the universe has a deep, testable history extending far beyond human memory or intuition. We have learned that space expands without expanding into an external room. We have learned that ancient radiation still crosses the sky, carrying evidence from a young and incandescent cosmos. We have learned that the simplest seeming beginning was exceptionally ordered, and that its order shaped the arrow of time. We have learned that vacuum, matter, radiation, geometry, and time are subtler than ordinary language suggests. We have learned that singularities mark the limits of current descriptions rather than established moments of creation. We have learned that quantum gravity may transform concepts previously treated as permanent foundations. We have learned that serious models can differ radically while remaining subject to evidence, consistency, and possible failure. The farther we push toward origins, the less secure our inherited images become. The frontier does not offer a final answer yet. It offers sharper questions, stronger constraints, and a clearer sense of what remains unknown. Perhaps the most profound possibility is that space, time, causation, vacuum, and even nothingness are emergent concepts. They may be tools that become meaningful only within a universe already rich enough to support relations, observers, and records. If so, Asking what existed outside or before everything may be like asking which direction lies north of the North Pole. The grammar seems familiar, but the question imports a framework that has reached its own boundary. That possibility should not end inquiry. It should refine inquiry, directing it toward theories capable of explaining how familiar concepts arise from deeper physical structure. Future observations may detect primordial gravitational waves, unusual cosmic correlations, subtle curvature, or signatures that distinguish competing early histories. Future quantum gravity theories may reveal whether time is fundamental, emergent, bounded, cyclic, or transformed beyond present language, or the final boundary may remain partly philosophical, because explaining total reality differs from explaining events within reality. We cannot know which outcome awaits, but uncertainty is not empty darkness. It is a map of questions drawn from real evidence, disciplined imagination, and the willingness to revise even our oldest assumptions. From a small planet orbiting an ordinary star, conscious matter has learned to reconstruct a universe nearly 14 billion years old. We have measured faint microwave photons that began their journey before galaxies, planets, or life existed. We have read elemental ratios forged in the first minutes. We have mapped galaxies whose light reveals cosmic expansion and the growth of structure across immense intervals. We have used equations born in human minds to test the behavior of space, matter, energy, and time. This achievement does not place us outside the universe. It makes us one of its temporary ways of becoming aware of its own deep past. The observers asking what preceded the bang are made from atoms formed in ancient stars. Their brains, instruments, and questions emerge from the same cosmic evolution they now investigate. That fact does not solve the origin mystery. It gives the mystery a human scale. We are not witnesses standing before creation's door. We are late arrivals within a vast unfolding, listening for echoes from a threshold our concepts can barely approach. Seen from Earth, the scale of this accomplishment is almost disorienting. Radio telescopes detect a glow only a few degrees above absolute zero, arriving from every direction like a cooled ember surrounding the night. Computers then separate that ancient signal from nearer stars, dust, and instrument noise. Within the remaining pattern lie clues to conditions before any galaxy shone. A species born late in cosmic time has learned to read that nearly erased inscription. The opening silence remains, but it no longer means an empty black void waiting around the universe. It names the place where certainty ends and the deepest questions begin. There may have been a finite beginning, a no-boundary origin, quantum tunneling, a bounce, a cyclic cosmos, eternal inflation, or an as-yet undiscovered framework. Evidence has not selected a winner. Any future answer will be judged not by comfort, grandeur, or verbal certainty, but by coherence and contact with reality. The Big Bang remains a magnificent discovery because it reveals the shared early history behind every star and atom we know. It is not a license to claim that science has explained why there is something rather than nothing. Its deeper lesson is stranger. The universe may not have emerged into space. Space may have emerged within the universe's own unfolding. Time may not be a river flowing outside cosmic history. It may be a feature of that history. And causation may not reach beyond time in the ordinary form our language assumes. Perhaps nothing did not start the Big Bang at all. Perhaps the real mystery is that the universe gave us the ability to imagine nothing, and then to look beyond it. Across this journey, the evidence has drawn a remarkably clear picture. Galaxies recede, ancient microwave light glows, and primordial elements preserve a hot cosmic past. The Big Bang is therefore not a guess about distant fire, but our strongest account of an expanding, evolving, observable universe. Yet every path beyond that early furnace, quantum vacuum, inflation, no boundary beginnings, bounces, cycles, and multiverses, encounters assumptions that physics has not yet explained. At the beginning, we asked whether the universe erupted from nothing, before space had a place and time had a first second. The honest answer is more mysterious. The Big Bang reveals a beginning to our known cosmic history, not proven creation from absolute nothing. Perhaps nothing was never an empty stage waiting to be filled, but a word stretched beyond the limits of human intuition. If space, time, and causation emerged together, then the universe did not merely begin within a mystery. It taught us what mystery means. Keep watching the sky, and keep testing its faintest signals, because every new measurement may reshape the question before answering it.